Tonight, humanity looks up at the stars and imagines crossing the darkness between them. Other worlds seem close enough to dream about, close enough to promise escape, discovery, even a new beginning. But what if the truth is far harsher? What if the distance between stars is not just difficult, but almost impossible for a species like ours to survive? From the speed of light to deadly radiation from fragile human biology, to the crushing scale of interstellar space, this is the quiet and unsettling reason humanity may never truly reach another star. Before we begin, please like this video, subscribe to the channel, and join us for more deep journeys into the universe, far beyond the thin band of air surrounding Earth, beyond the moon, and the planets beyond the icy bodies that drift at the edge of the solar system. Space opens into a scale that steadily leaves ordinary human intuition behind. The observable universe extends across distances so large that language must borrow special units just to speak about them without drowning in digits. A light year is the distance that light travels in 1 year. It is not a measure of time, but of length, and even this large measure soon becomes small when applied to the broad structure of the cosmos. Galaxies gather in clusters, clusters gather in larger patterns, and between them lie enormous reaches where light spends millions or billions of years in transit. Humanity lives in a very small corner of this vast arrangement, on a rocky planet circling one ordinary star in one spiral arm of one galaxy, among many billions. In this outer view, the dream of interstellar travel begins not with machinery but with proportion. It begins with the plain relation between a small, short-lived species and an environment that is neither scaled to the body nor responsive to desire. On Earth, motion usually unfolds across ranges that life has evolved to manage. A person crosses a room in seconds, a city in hours, an ocean in days. Even the distance to the moon, though immense by everyday standards, still sits within a human framework of planning launch, transit, and return that can be imagined as a single mission. Interstellar space belongs to a different order. The separations between stars are so large that they resist comparison with the distances through which human history has been lived. The solar system itself offers a first lesson in this widening scale. Earth circles the Sun at a distance of about 150 million kilometers. Light from the Sun reaches Earth in a little more than 8 minutes. Neptune, the outermost major planet, travels around the Sun at an average distance of roughly 4.5 billion kilometers. Light takes several hours to cross that span. These are already large distances, and yet the solar system, even if it is extended to include the scattered icy bodies much farther out, remains only a tiny local structure around a single star. Once the eye steps beyond the Sun's immediate domain, the spacing between stars becomes the defining fact. The Milky Way contains hundreds of billions of stars. They are not packed together like grains of sand. They are widely separated, each one surrounded by vast intervals of dark space, containing only thin gas dust radiation and wandering particles. If the Sun were reduced in thought to the size of a small bead, the nearest stars would still lie far away across an emptiness that would dominate the model. The image is useful because it removes the false impression often created by diagrams where stars appear close only because a page or screen is small. Real interstellar geography is not crowded. It is sparse to a degree that makes distance the first and most stubborn reality. This is why the outermost region of the topic must begin with the observable universe, rather than with engines or ships. Before there is any question of design, there is the deeper question of setting. Humanity does not attempt movement through an open landscape filled with convenient stepping stones. It looks outward from inside a galaxy embedded in a universe whose great structures are governed by gravity expansion and long durations of cosmic time. The nearest galaxy of similar size, Andromeda, lies about 2.5 million light-years away. Light leaving that galaxy begins its journey long before human civilization takes its present form. Most galaxies visible in telescopes are vastly farther still. Even the light now entering observatories from the distant universe often began its travel before Earth existed in its present state. The cosmos is not merely large, it is old, and its size is inseparable from that age. Against this backdrop, the idea of crossing from star to star already reveals its severity. The problem is not simply that stars are far away, it is that all known human activity unfolds on timescales and energy budgets that evolved inside a sheltered planetary environment and a very compact local orbit around one star. Human bodies are brief in duration. Human institutions are often unstable across even a few generations. Human technology changes rapidly, but it also depends on layers of supply maintenance industry and knowledge distributed across the surface of one world. Interstellar travel asks whether such a species can project itself meaningfully across distances that naturally belong to the motion of light and the lifetimes of stars rather than the lives of animals. The outer cosmos also corrects another common impression. Space is often imagined as freedom because it lacks roads, borders mountains and seas in the terrestrial sense. From a distance it seems open in every direction. Yet openness at cosmic scale becomes a kind of confinement. There is no hidden shortcut visible in ordinary physics, no known way to fold vast separations into easy passage for matter, no natural bridge from one star to another that resembles a current or a wind carrying vessels between ports. The stars shine across gulfs that remain gulfs. Light crosses them because light is woven into the structure of space and time in a way matter does not surpass. Human beings built from matter and dependent on complex chemistry do not move through this setting with the simplicity of a beam. In the observable universe, many processes are grand and patient. Stars form over millions of years from cold clouds of gas and dust. Galaxies rotate over spans beyond recorded history. Light from remote objects crosses the cosmos, while entire species appear and vanish on single planets. Human civilization, by contrast, is recent. Agriculture is recent. Industry is recent. Spaceflight is extremely recent. The first journeys beyond Earth orbit belong only to the latest moment in the long timeline of cosmic history. This does not make human effort insignificant, but it does place it inside a scale where optimism alone has little force. Nature is not impressed by aspiration. Distance does not soften because a species has learned mathematics and built rockets. From this outer view, impossibility does not yet mean absolute prohibition. It means that the baseline conditions are already unfriendly to the project before any detailed obstacle is named. A challenge can become impossible in practice when too many severe conditions align at once, even if no single law states a simple ban. Interstellar travel may belong to this category. The universe presents a setting in which stars are separated by immense distances, useful speeds appear bounded, and the beings proposing the journey are fragile, short-lived, and dependent on intricate support systems. At the largest scale, the mismatch is plain. One side of the comparison is cosmic distance measured in light years and structured by astrophysical time. The other is humanity, a planetary species only beginning to move beyond its cradle. Seen from the widest possible region, the question is therefore calm and severe. It is not whether imagination can conceive of other stars, nor whether curiosity can point toward them. Both are easy. The harder fact is that the observable universe sets the stage first. It offers breadth without mercy, age without urgency, and distance without regard for the hopes of those who measure it. In that setting, the first reason interstellar travel may be impossible for humanity is simply that the universe is built on scales profoundly different from those in which human life, human machines, and human history can comfortably endure. Within the immense breadth of the Milky Way, the solar system occupies a small and ordinary place. The Sun is a single star among many moving through the galaxy, with its own long orbital path, accompanied by planets, small bodies, dust, magnetic fields, and a wide cloud of matter shaped by solar gravity and solar wind. Yet the most important fact about this neighbourhood when interstellar travel is considered is not the richness of the Sun's immediate domain. It is the spacing of the nearest other stars. Once attention narrows from the broad galaxy to the local stellar neighbourhood, the abstract scale of the cosmos becomes a set of measured separations, each one large enough to turn a destination into a span of years, centuries, or more, depending on the speed assumed. The nearest known star system to the Sun is Alpha Centauri, a group of stars a little more than 4 light-years away. This is a close neighbour only by galactic standards. In human terms, it remains almost beyond ordinary comparison. Light moving at the fastest speed known in nature takes more than 4 years to cross the distance. A spacecraft moving far slower would need much longer. Even a vehicle travelling at a small fraction of the speed of light would spend decades in transit before arrival, and that estimate would describe only the cruise across the distance itself, not the full burden of launching, acceleration, survival guidance, and any slowing needed at the far end. The local neighbourhood therefore transforms a remote dream into arithmetic. The nearby stars can be named, mapped, and studied, but their nearness does not make them near in a practical sense. This local region includes stars of different kinds. Some are bright, massive, and comparatively short-lived. Others are smaller, cooler, and far more common. Many of the stars close to the Sun are red dwarfs, small stars that burn their fuel slowly and can remain stable for very long periods. Some nearby stars exist in multiple systems where 2 or more stars orbit one another. Others host planets, including worlds, detected through small changes in starlight or in stellar motion. These discoveries deepen scientific interest because they show that planets are common and that some reside within temperature ranges where liquid water might exist under suitable conditions. Yet every such finding also sharpens the central difficulty. The more carefully nearby worlds are examined, the more clearly the separation remains in view. Knowledge of a place does not reduce the distance to it. The local stellar neighbourhood is not arranged in a neat line of stepping stones. The stars are distributed through 3-dimensional space, each with its own motion, age, composition, and environment. Over long intervals, they drift relative to one another. The nearest star today is not guaranteed to be the nearest over all cosmic time. Some stars gradually approach, others recede. These motions matter to astronomy, but they do not rescue the problem. The changes are slow on the timescale of human planning, and the distances remain severe. Even if a target star were to pass somewhat closer over many thousands of years, the gain would still leave a journey of extraordinary length for any craft built by present or near-future methods. The Sun's own planetary system offers another point of contrast. A probe sent to the outer planets may require years or more than a decade to arrive, and such missions already demand patience, precision, and durable engineering. Communication delays grow from minutes to hours as the craft moves farther from Earth. Instruments must survive cold radiation and mechanical strain. Yet these missions remain fully inside the Sun's gravitational and practical sphere. They can still draw guidance from Earth with delays that, though inconvenient, remain meaningful within a single mission lifetime. Interstellar travel crosses out of that familiarity. The nearest stars lie not several light hours away, but several light years away. This is a multiplication of scale so great that the old analogies begin to fail. A voyage to another star is not simply a longer planetary mission, it is a different class of undertaking. Astronomers describe distances to nearby stars with great care using methods such as parallax, in which a star's position appears to shift slightly against the distant background as Earth moves around the Sun. This method provides one of the clearest direct measures of stellar distance. It reveals with quiet precision that the local stars are not poetic abstractions but fixed points in a real geometry. The map is trustworthy. The numbers are not guesses in a broad sense. The nearest targets truly are several light years away. That certainty matters because it removes any comforting hope that ignorance is exaggerating the difficulty. Better measurement has not made the local stars more accessible. It has only made their remoteness more exact. Among the nearby stars, some attract special attention because they appear to host planets in or near the temperate zone around the star where liquid water might exist. This does not mean that such worlds are Earth-like in a full sense. A planet may lie at a suitable distance from its star yet still be hostile because of atmosphere radiation chemistry, tidal locking magnetic weakness, or stellar activity. Many red dwarfs, for example, produce flares and energetic emissions that may challenge planetary habitability. Observations indicate that potentially rocky planets exist around such stars, but it remains uncertain how often those worlds maintain long-term surface conditions suitable for complex life. In the local neighborhood, then, even the most attractive destinations are not proven homes. They are distant possibilities. This uncertainty adds weight to the distance problem. A journey inside the solar system usually proceeds toward bodies that are already known to exist in clear detail. Their positions, masses, and basic environments can be measured with increasing confidence before arrival. A journey to a nearby exoplanet would be different. It would aim toward an object inferred through careful data, partly characterized but not intimately known. The travelers would commit enormous time and resources before complete certainty about the destination could be obtained. In ordinary exploration on Earth, uncertainty has often been acceptable because travel times were limited and return remained conceivable. In the interstellar neighborhood, uncertainty stretches across decades or longer. Error becomes more punishing because correction comes too late. The local stars also expose the difficulty of defining success. Reaching another star in a symbolic sense is one thing. Reaching it in a useful sense is another. A fast flyby could gather data, but if the craft passes through the target system at very high speed, the observation window is brief. A slower arrival would allow fuller study, yet slowing down requires additional energy, time, and equipment. In this neighborhood of nearby suns, a mission must not only cross the gulf, but also arrive in a controlled way if it is to do more than glance. Thus, the distance to the closest stars is not merely a matter of one long straight line. It is bound to the full structure of departure, cruise arrival, and purpose. This measured region around the Sun therefore strips away the softness of imagination. It replaces the broad grandeur of the galaxy with named stars, exact distances, and concrete implications. Alpha Centauri, Barnard Star Wolf 359 Leyland 21185, Sirius Epsilon, Eridani Tau Ceti, and other nearby stars belong to a local map that science can describe with increasing detail. Yet the map does not become friendlier as it becomes clearer. It becomes sterner. Each star is close enough to invite thought and far enough to resist ordinary reach. Each one sits within a span that turns the fastest known signal into years of travel. In this local neighborhood, the case for possible impossibility becomes sharper. The problem is no longer hidden inside the immensity of the whole universe. It is present already among the nearest destinations. Humanity does not first fail at the edge of the galaxy. It may fail at the threshold of the nearest stars because even the closest targets demand durations, reliability, energy, and commitment that strain the scale of human life and human systems. The stars around the Sun are neighbours only in astronomy. For travellers made of flesh, metal, and limited time, they remain profoundly far away. Between one star and another there appears at first glance to be almost nothing. The darkness between stellar points suggests emptiness so complete that travel through it might seem simpler than travel through air or water. There are no storms in the ordinary terrestrial sense, no mountains to cross, no oceans to navigate, no ground to resist motion. This impression is useful only from a great distance. When attention settles on the actual substance between stars, the interstellar medium emerges as a real environment with structure, particles, fields, and radiation. It is exceedingly thin, but the journey it would confront is exceedingly long. Over such length, even sparse matter becomes consequential. The interstellar medium consists mainly of hydrogen, with smaller amounts of helium and trace heavier elements, along with dust grains, magnetic fields, and energetic particles known as cosmic rays. It is not evenly distributed. Some regions are comparatively denser, with cold clouds of gas and dust. Other regions are hotter and more rarefied, shaped by shock waves from ancient stellar explosions or by stellar winds flowing outward from active stars. In the broadest average sense, the amount of matter in a cubic centimetre of interstellar space can be very small when compared with any earthly standard. Yet a spacecraft attempting to cross several light years would not pass through 1 cubic centimetre. It would pass through an immense column of space-meeting particle after particle, grain after grain over years or decades of motion. This matters because speed transforms small things into dangerous things. At ordinary human speeds, a dust grain is trivial. At a substantial fraction of the speed of light, the same grain carries energy sufficient to damage surfaces, penetrate shielding, or produce violent local effects on impact. Even single atoms and ions can become a persistent source of erosion when they strike a fast-moving craft over long periods. The interstellar medium is too thin to resemble a fluid through which a spacecraft ploughs in any familiar way, but it is not so thin that it can be ignored. A journey of interstellar length multiplies every small encounter until the cumulative burden becomes one of the mission's central physical conditions. Dust is especially important. Interstellar dust grains are tiny solid particles composed of materials such as silicates, carbon-rich compounds, and ices under some conditions. They help shape the light seen by astronomers because they absorb and scatter starlight. In an astronomical image, they may appear gentle as dimming reddening or dark lanes crossing brighter regions. For a fast-moving vehicle, they are less gentle. Their small size does not protect the craft if the relative velocity is extreme. A grain striking at high speed behaves less like dust in a room and more like a concentrated projectile. The probability of such impacts depends on the local density of dust along the route, which is not perfectly uniform and cannot be known everywhere in full detail. Observations indicate broad patterns, but they do not remove the hazard. Gas presents a different form of challenge. Individual atoms and ions are minute yet at high speed. They collide with the spacecraft's surface with substantial energy. Over time they can heat exposed materials, sputter atoms away from structural surfaces, damage electronics, and complicate the stability of any unshielded systems. They also raise a deeper problem for mission design. Shielding sufficient to protect against relentless particle impact adds mass. Added mass then raises the energy needed for acceleration and deceleration. This is a recurring pattern in interstellar thinking. Protection against one difficulty often enlarges another. The medium between stars is thin, but to survive it at high speed, a craft may need heavy protective measures, and those measures may then make the journey harder to begin. The interstellar medium also contains magnetic fields and charged particles. These fields are weak by laboratory standards, yet they thread through the gas and shape its behavior over large distances. Charged particles spiral along magnetic structures, and shock waves from stellar events can accelerate particles to very high energies. Cosmic rays, which are energetic particles arriving from a range of sources, form part of the radiation background of space. Within the solar system, astronauts and spacecraft already face radiation hazards from the sun and from galactic cosmic rays. Beyond the stronger protective influence of Earth's magnetic field and atmosphere, the concern grows. Over an interstellar voyage lasting many years, accumulated radiation dose becomes a serious issue for electronics and for living tissue. The interstellar medium is therefore not only a matter of collision, it is also a field of invisible energetic exposure. Astronomy shows that the space around the Sun lies inside a local region of relatively low-density gas, often called the local bubble, likely shaped by ancient supernova activity. The solar system also moves through a small local cloud within this wider structure. Such findings reveal that the Sun's neighbourhood is part of a dynamic and historically shaped medium, not an unchanging void. Conditions vary from region to region. Temperature, ionization density, and dust content shift across interstellar space. A spacecraft route could in principle be chosen to avoid denser clouds, but the general problem would remain. Even the more rarefied regions are not empty enough to remove cumulative interaction over light-year distances. This is one reason why some interstellar mission concepts imagine a protective forward shield, sacrificial material layers, electromagnetic deflection methods, or even a leading cloud of particles launched ahead of the craft to intercept incoming matter. Such ideas are physically motivated, but each carries costs and unresolved technical demands. A solid shield must survive repeated impacts without catastrophic cracking or ablation. An electromagnetic system works mainly on charged particles and does not easily solve the dust problem. Pre-deployed protective cloud would require precise control and additional mass. None of these responses belongs to fantasy in a simple sense, yet none removes the underlying truth that the medium itself is an obstacle that becomes more severe as speed rises. The interstellar medium also affects navigation and detection. Spacecraft traveling across several light-years would need to orient themselves with extraordinary accuracy. Tiny deviations in angle can grow into enormous positional errors over great distances. Meanwhile, the vehicle must survive in a region where external references of faint signals are delayed, and the environment may alter sensors through radiation damage or surface degradation. The medium does not merely strike the craft. It wears at the systems by which the craft understands its own path. This region between stars therefore changes the emotional image of interstellar travel. The darkness is not a clean corridor. It is a sparse physical environment that resists passage not through thickness, but through persistence. Earth teaches that resistance usually comes from density. Water pushes hard because it is heavy. Air burns because it is compressed at high speed. Interstellar space teaches another lesson. Resistance can also arise from duration and velocity. When the route is measured in light years and when useful travel seems to require extreme speed, the tiniest particles gain practical power. Scientific knowledge supports this sober view. The interstellar medium is not a speculative concept inserted to discourage ambition. It is directly studied through spectroscopy, radioastronomy, infrared observations, ultraviolet measurements and models grounded in the physics of gas, dust and plasma. Observations indicate its properties with increasing detail, though small-scale structure and route-specific hazards remain imperfectly known. That uncertainty itself matters. A mission designed for one expected environment may encounter another. The space between stars is not only hostile in a general sense, it is varied enough to complicate exact prediction. In the local neighbourhood of the Sun, then, the gulf between stars is more than distance alone. It is filled with thin matter, energetic particles, radiation, and microscopic solids that become dangerous when met at extraordinary speed for extraordinary spans. The interstellar medium does not forbid travel by a single simple law. Instead, it turns the journey into a continuous exposure problem. A vehicle must endure not one great event, but countless small events that accumulate across years, eroding surfaces, threatening systems, and demanding shielding that then burdens propulsion. What first appears to be emptiness becomes, under scientific attention, a difficult terrain of another kind. The space between stars is dark and sparse, but it is not gentle. In the space between stars, motion encounters its deepest known restraint not in machinery, but in the structure of nature itself. A spacecraft may be made stronger, larger, lighter, or more efficient by improved engineering, but all such changes still unfold within a framework that modern physics describes with unusual consistency. In that framework, the speed of light in vacuum stands as the known upper limit at which information and causal influence travel. Light does not merely happen to move very fast. Its speed is woven into the relations between space-time energy and momentum. This makes it more than a practical benchmark. It becomes a boundary that shapes what any material traveller can do. For ordinary daily life, this limit is invisible. Human bodies, vehicles, winds, and waves move so slowly compared with light that the difference between familiar intuition and physical law remains hidden. A person throwing a stone, a jet crossing a continent, or a planet orbiting a star all inhabit a low-speed world where Newtonian ideas work very well. Distances add in simple ways, time appears to pass equally for all nearby observers, and mass seems stable and separate from motion. As speed rises toward a significant fraction of the speed of light, these approximations begin to fail. Space and time no longer behave in the simple common-sense manner learned from daily experience. The rules of special relativity begin to dominate. Special relativity, developed in the early 20th century, rests on a few central principles. One of them is that the laws of physics are the same for observers moving at constant speed relative to one another. Another is that the speed of light in vacuum is the same for all such observers. These principles lead to results that are now supported by extensive experiment and observation. Time intervals depend on motion. Length along the direction of motion depends on motion. Energy and momentum are linked to speed in ways that become increasingly severe as velocity approaches the speed of light. Most importantly for interstellar travel, no object with rest mass can be accelerated to the speed of light. As speed rises, the energy required continues to grow without reaching a final, finite value that would complete the crossing to light speed. This fact changes the character of travel between stars at the most fundamental level. It means that the great distances measured in light years cannot be overcome by simply declaring a sufficiently powerful engine. There is no known engineering path that turns matter into a light-speed traveller. A spacecraft can, in principle, move arbitrarily close to the speed of light, but each further increase demands disproportionately more energy. The remaining gap becomes harder to close, not easier. In practical terms, this means that every proposed interstellar mission must accept that the travel time, as measured in some frame, remains at least several years to the nearest stars and far longer to most others. The cosmic map does not yield to enthusiasm because the speed ceiling is built into the map itself. This upper limit also governs communication. Signals sent by radio laser or any other known electromagnetic means travel at the speed of light in vacuum. No message sent from a spacecraft to Earth arrives faster than that. No instruction from Earth reaches the spacecraft sooner. Thus, even if a vehicle could move extremely fast by human standards, it would still exist inside a communication structure shaped by light speed delay. A craft 4 light-years away cannot converse with Earth in any immediate sense. A message sent outward would take years to arrive, and any reply would take years more. The speed limit therefore restricts not only transport but relationship. Interstellar separation becomes a separation in time as much as in space. The limit has another consequence that often misleads imagination. Fiction sometimes treats faster-than-light travel as if it were merely a future technology waiting to be invented, much as powered flight once awaited the development of engines and airframes. The known physics does not support that comparison. There are speculative ideas in theoretical physics involving unusual space-time geometries, such as wormholes, or metric distortions sometimes discussed in the context of warp concepts. These arise from mathematical structures within general relativity, but their possible physical realization remains entirely uncertain. They often require exotic conditions such as negative energy densities or stable forms of matter not known to exist in the required way. At present, there is no empirical evidence that humanity can build or use such mechanisms. Observations support relativity with extraordinary precision in accessible conditions, while routes around the light speed limit remain hypothetical and unresolved. Because of this, the light speed boundary is not best understood as pessimism. It is a statement of the present scientific description of the world. The same physics that allows modern electronics particle accelerators, global navigation systems, and precise astronomy also states that material bodies cannot simply outrun light. Interstellar travel proposals that respect established knowledge must therefore operate beneath that ceiling. Once that is accepted, the problem becomes one of fractions. How close can a spacecraft come to light speed for how long, with what energy cost and with what consequences for structure shielding and occupants? The distance between stars then remains enormous, because even a substantial fraction of light speed is still not light speed. To see the weight of this, it helps to return to the nearest stellar destinations. If a target lies a little more than 4 light-years away, then travel at 1/10 of the speed of light would already be an achievement beyond any human vehicle ever built. Yet even that would imply a journey of more than 40 years in the frame of those left behind, not counting the full demands of speeding up and slowing down. Travel at 1/5 of the speed of light would reduce the time, but still leave a mission measured in decades. Faster motion would require even more severe energy and shielding demands. The limit set by light does not merely cap the maximum. It forces every plausible mission into a region where the durations remain long enough to burden engineering, biology, and civilization. Relativity also alters the experience of time aboard a fast-moving craft. A traveller moving at very high speed may age less than those who remain on Earth. Because of time dilation, the difference in elapsed time between frames in relative motion. This is a real effect measured in experiments with fast particles and precise clocks. Yet it does not remove the light speed barrier. It does not allow a ship to reach a distant star instantly. It only means that under very high-speed travel, the passage of time aboard the vessel can differ from the passage of time on Earth. The outside world still waits according to its own clocks, and the energy needed to produce the required speeds remains formidable. Time dilation may soften one aspect of duration for travellers, but it intensifies the separation from home and leaves the main physical burden intact. In this region of the topic, the central lesson is simple and severe. The stars are not merely far away by accident. They are embedded in a universe where the maximum speed of matter and information is tightly constrained by physical law. Human beings often solve problems by going faster, building larger, or organizing better. Those methods have genuine power, but they do not erase fundamental limits. The light speed boundary means that interstellar travel cannot be turned into an ordinary transport problem. It remains a confrontation with the architecture of space and time. This is why the possibility of impossibility begins to harden here. Earlier regions reveal scale and distance. The interstellar medium reveals environmental hazard. This region reveals something even more decisive. The journey is not only hard because the stars are far and the path is rough. It is hard because nature appears to forbid the one shortcut that would truly transform the situation. Humanity may build better engines. It may develop new materials. It may improve autonomy, shielding, and durability. Yet as long as known physics holds, every such improvement still unfolds below the speed of light within a cosmos, where even the nearest stars remain years away for light itself, and longer still for anything made of matter. Once motion is bound beneath the speed of light, the question of energy becomes central. To cross the distances between stars within any duration that can be meaningfully discussed, a spacecraft must reach speeds far beyond those used in present-day missions. Increasing speed, however, is not a simple matter of adding more fuel in a linear way. The relationship between speed and energy is such that each increment in velocity requires a greater addition of energy than the last, especially as the velocity approaches a significant fraction of the speed of light. This transforms the design of an interstellar journey into a problem where energy demand grows steeply, and where the source, storage, and control of that energy become defining constraints. In everyday motion, the energy needed to accelerate an object grows with the square of its speed. This relation holds well at low speeds and is familiar in the operation of vehicles, projectiles, and machines. At higher speeds, especially those approaching the speed of light, the situation becomes more complex. The energy required does not merely continue to follow a simple square relation. Instead, it increases more sharply, reflecting the relativistic connection between energy and momentum. As a result, pushing a spacecraft from 1/10 of the speed of light to 2/10 demands far more than double the energy. Each additional fraction of light speed carries a heavier cost. For an interstellar mission, this has immediate consequences. Consider a vehicle of substantial mass large enough to contain structure-shielding guidance systems and possibly life support. To accelerate such a vehicle to even a modest fraction of light speed would require an amount of energy comparable to or exceeding the total energy production of human civilization over long periods. This is not a matter of inefficiency in current technology alone. It is rooted in the physical scale of the task. A massive object must carry a great deal of kinetic energy when moving very fast, and that energy must come from somewhere that the vehicle can access and control. Energy must also be supplied not only for acceleration but for deceleration. A journey to another star that ends in a rapid flyby is scientifically limited. To enter a target system in a useful way, a spacecraft must slow down. This effectively doubles the energy problem because energy used to speed up must be matched by energy used to slow down, unless some external method of braking is available. Concepts such as using the radiation pressure of a star, magnetic interaction with stellar winds, or gravitational assists within the target system may offer partial help, but they do not eliminate the need for a substantial energy budget carried by or available to the spacecraft. The source of energy becomes a separate and equally difficult issue. Chemical propulsion, which powers most current rockets, is far too limited in energy density to support interstellar travel at meaningful speeds. Nuclear fission offers a higher energy density but still falls short when the required speeds and masses are considered. Nuclear fusion, the process that powers stars, promises greater energy release per unit mass and has long been studied as a possible basis for advanced propulsion. Yet controlled fusion suitable for propulsion remains an unsolved engineering challenge. Even if achieved, the efficiency with which fusion energy could be converted into directed thrust and the amount of fuel that must be carried present further complications. More extreme concepts consider antimatter, in which matter and antimatter annihilate to release energy with very high efficiency. In principle, this offers an energy density far beyond chemical or nuclear processes. In practice, antimatter is extraordinarily difficult to produce, store and handle. The amounts that can be created in laboratories are extremely small, and containment requires conditions that prevent contact with normal matter. Scaling this to the quantities needed for interstellar propulsion introduces challenges that remain unresolved. Observations and experiments indicate that antimatter obeys the same fundamental physics as matter, but they do not yet provide a pathway for its large-scale practical use in propulsion systems. Energy storage and management add further layers of difficulty. A spacecraft must not only carry or access a vast energy supply, but must also release it in a controlled manner over long durations. The conversion of stored energy into thrust involves losses. Waste heat must be managed and radiated away, which is difficult in the cold vacuum of space where heat transfer relies on radiation rather than conduction or convection. Large radiators add mass and complexity. If heat is not removed effectively, systems can fail. Thus, the energy problem is not only about quantity, it is also about handling conversion and stability over the full course of a mission. Another aspect of the energy burden lies in the mass of the energy source itself. Any fuel carried by the spacecraft contributes to the total mass that must be accelerated. This creates a feedback loop. More fuel increases mass. Increased mass requires more energy to accelerate. More energy requires more fuel. This loop is not easily broken. It is a central feature of rocket-based propulsion and one of the reasons why interstellar travel poses such a severe challenge. Alternative concepts that reduce or avoid carrying fuel, such as beamed energy propulsion, where energy is supplied from a distant source, like a powerful laser array, shift the problem rather than remove it. They require infrastructure of enormous scale, precise alignment over vast distances and reliable operation across long times. The scale of energy involved also raises questions about feasibility at the level of civilization. Even if a particular technology could in principle supply the required energy, the effort to build, maintain and operate such a system would be immense. It would demand sustained commitment across many years or generations, stable economic and social conditions, and coordination of resources on a global scale. Observations of human history show that such stability is not guaranteed. Large projects can falter due to political change, economic strain, or shifting priorities. An interstellar mission would likely exceed any previous project in duration and complexity, making it vulnerable to disruptions that are difficult to predict or control. Scientific understanding provides a clear picture of the energy landscape. It does not suggest that energy requirements can be reduced by clever design alone to a level that makes interstellar travel straightforward. Efficiency improvements are always valuable, but they cannot change the fundamental relation between speed, mass, and energy. Observations and theory agree that high-speed travel across light-year distances carries a steep energy cost. It remains uncertain whether future discoveries in physics could alter this picture in a significant way. At present, no evidence indicates a mechanism that would allow large masses to be accelerated to near-light speeds with modest energy. In this region, the difficulty of interstellar travel becomes grounded in measurable quantities. Distance sets the scale of the journey. The speed of light sets the upper bound on motion. Energy sets the price of attempting to approach that bound. Together they form a system in which each element reinforces the others. A long distance demands high speed to reduce travel time. High speed demands large energy. Large energy demands substantial infrastructure, fuel and management. Each step introduces further constraints that must be solved simultaneously. The calm conclusion that emerges here is not dramatic but steady. Interstellar travel may be impossible for humanity, not because it is forbidden by a single clear rule, but because the energy required to make it practical may lie beyond what human systems can reliably generate, control and sustain. The universe allows motion, but it sets a cost that rises sharply as ambition grows. In the quiet accounting of energy, the journey between stars becomes a balance that may never settle in favor of the traveler. Energy alone does not move a spacecraft. To change motion in a controlled way, a vehicle must exchange momentum with something. In familiar rocketry, this is done by expelling mass in one direction so that the vehicle moves in the other. The idea is simple and deeply reliable. It does not require air roads or an external surface. It works in vacuum because momentum is conserved. Yet the same principle that makes rockets possible also makes them difficult at large scale. A rocket must carry the material it intends to throw away. For long journeys requiring large changes in speed, this requirement grows into one of the most severe constraints in all of astronautics. This difficulty can be described with a plain image. A traveller trying to move a heavy cart across a great distance must carry not only provisions and shelter, but also the ground needed for each next step. The more steps required, the more ground must be brought along. A rocket faces a similar burden. The propellant expelled at the start of the mission has to be lifted and accelerated along with the rest of the spacecraft before it can be used. This means that fuel for later stages becomes part of the load for earlier stages. As the demanded change in speed increases, the amount of propellant required rises rapidly. This relationship is not a minor inconvenience in rocket design. It is a central law-like feature of reaction propulsion. The classic rocket equation expresses this relation. It connects the change in speed a rocket can achieve with the speed at which it expels propellant, and with the ratio between its initial mass and its final mass after propellant has been spent. The equation is simple in form but severe in implication. To gain a larger change in speed, a rocket must either throw exhaust much faster or begin with a much greater mass compared with the mass that remains after the burn. Because exhaust speed is limited by the propulsion method, large mission demands often force the mass ratio upward. The result is a vehicle that may begin as an enormous structure whose useful payload is only a tiny fraction of the whole. This problem already shapes missions within the solar system. Launch vehicles on Earth are mostly propellant by mass. Only a small part of the initial launch mass becomes the spacecraft, and only a smaller part becomes useful payload. Staging helps by discarding empty tanks and engines along the way, reducing dead weight. Yet even with staging, the mass penalties are substantial. An interstellar mission would magnify this difficulty. To reach another star in less than many centuries, the spacecraft would need a change in speed vastly beyond that of ordinary planetary missions. If the same basic rocket logic is used, the required starting mass can become so large that the design loses practical meaning. Chemical rockets are the clearest example of this limit. They expel exhaust at speeds far too low to support meaningful interstellar travel for substantial payloads. Even if an enormous chemical rocket could be assembled, the mass ratio needed to reach a useful fraction of the speed of light would be absurdly high. the vehicle would be dominated almost entirely by propellant, with barely any room left for structure-shielding guidance or human support. Nuclear thermal rockets and electric propulsion systems can improve exhaust speed, but not by enough to erase the mass problem for interstellar scales. They are valuable for some missions inside the solar system, yet they do not convert the journey to another star into a manageable rocket task. Fusion-based rocket concepts attempt to address this by using a process with much higher energy density and potentially much higher exhaust speed. Designs studied over decades have included pulsed fusion magnetic confinement ideas and inertial approaches. In theory, these methods could reduce the mass ratio compared with chemical propulsion. In practice, they still face very hard constraints. Fusion itself remains difficult to sustain and control. The machinery needed to ignite confine and direct the reaction adds mass. The fuel may require storage under demanding conditions. Much of the released energy may not turn into useful directed exhaust. The rocket equation still applies. Better exhaust speed helps, but unless it becomes extraordinarily high, and the rest of the vehicle remains light, the mass burden remains heavy. Antimatter rockets are often described as a possible escape from this trap, because annihilation can release very large amounts of energy from small amounts of mass. Yet here as well, the situation is less generous than it first appears. Antimatter must be produced, stored and prevented from touching ordinary matter until the correct moment. The systems required for confinement and controlled use would themselves add mass and complexity. In addition, not all of the reaction products are easy to direct into thrust. Some are neutral particles or high-energy radiation that are difficult to turn into efficient propulsion. Even an extremely advanced reaction rocket based on antimatter would not step outside the basic logic of carrying reaction mass and expelling it. It might ease the burden, but it would not abolish it. One response to this difficulty is to imagine collecting reaction mass from the interstellar medium during flight, rather than carrying it all from the start. The best-known family of ideas along these lines uses an immense magnetic scoop to gather sparse hydrogen from space for fusion propulsion. The appeal is clear. If the spacecraft can use the medium around it as fuel, the launch mass may become much smaller. The problem lies in the thinness of that medium and in the drag introduced by the collection process. Interstellar gas is so sparse that a scoop large enough to gather useful amounts of matter may be physically unrealistic. The magnetic structures required would be vast, and the interaction with the incoming medium could create resistance that offsets or exceeds the gained thrust. Studies suggest that such designs face very serious obstacles, and it remains uncertain whether they could operate as imagined. Another response is to abandon onboard propulsion after launch and rely on external energy such as powerful lasers pushing a sail. This changes the architecture dramatically, but it also reveals how central reaction mass has been to rocket thinking. A sail system can avoid carrying large amounts of fuel during the acceleration phase, yet if the mission is to deliver a substantial payload and arrive under control, the problem returns in another form. A very light probe may be accelerated this way in principle, though even that remains technically challenging. A crude or heavy vehicle would demand a sail and beam system of extraordinary scale. If braking at the destination is required, new systems must be provided there or carried along, reintroducing mass and complexity. The old burden never vanishes entirely. It shifts position in the design. For human missions, the reaction mass problem becomes even harder, because the payload is not merely an instrument package. It may include shielding habitat volume, life support, redundancy repair capability and supplies or recycling systems. All of that useful mass sits above the propulsion system and must be accelerated together. A robotic probe can sometimes accept fragility and brevity. A human mission cannot do so easily. It must preserve life through a long transit which pushes payload mass upward. As payload mass rises, the required propellant rises. As propellant rises, the launch system grows. As the system grows, the engineering challenge deepens. This compounding structure is one reason interstellar travel may fail not at one single point, but through the interaction of many hard requirements that all intensify one another. The history of spaceflight offers a quiet lesson here. Rockets have allowed humanity to leave Earth, orbit the planet, visit the Moon, and send instruments across the solar system. They are among the most powerful machines ever built. Yet their power comes with this obvious visual truth: most of what rises from the launch pad is fuel. The useful portion is small and carefully protected inside a vast disposable machine. Interstellar travel asks this same method to operate across a scale millions of times more severe in duration and demanded speed. It is therefore reasonable to ask whether the rocket principle, so successful locally, may simply be the wrong foundation for travel between stars when the travelers are heavy, fragile, and slow to replace. The reaction mass constraint does not absolutely forbid all missions in all imaginable futures. Small probes driven by external beams or exotic advanced engines may remain objects of study. But for humanity as a travelling species, the problem is sharper. A starship must not only move, it must move while carrying itself. It must lift and accelerate the means of its own acceleration, then survive the long consequence of that decision. This is the inward logic of rockets, and it becomes harsher as the journey lengthens. In this region of the topic, the possibility of impossibility becomes mechanical and exact. The obstacle is not only distance, not only energy, but the burden of mass that any reaction-driven craft must bear from the beginning. Rockets work because they throw matter away. For interstellar travel, they may fail because too much matter must be brought along before any of it can be thrown. When the burden of ordinary rockets becomes clear, attention turns toward propulsion concepts that seem to stand further from present practice. These ideas often carry an air of release, as though the old constraints of fuel mass and limited exhaust speed might finally loosen. Some are grounded in established physics but demand engineering far beyond current capability. Others depend on conditions that have not been demonstrated outside theory. In every case, the question is not whether imagination can propose a mechanism. It is whether the mechanism can move from physical possibility in principle to reliable operation across interstellar distance. In this region, the study of exotic propulsion becomes a slow sorting of what is plausible, what is unresolved, and what may never become practical for humanity. One of the most discussed alternatives is the light sail, or more generally the sail driven by radiation pressure. Light carries momentum, and when it reflects from or is absorbed by a surface, it can impart a small push. In the solar system, sunlight itself can produce this effect, and solar sails have been demonstrated in space on a limited scale. For interstellar purposes, the concept usually shifts from sunlight to an intense artificial beam, often imagined as a powerful laser array based far from the spacecraft. The attraction is clear. A sail can be accelerated without carrying large stores of onboard propellant, which seems to bypass the harshest part of the rocket equation. Yet this gain comes with strict conditions. The sail must be extremely light, highly reflective, and stable under intense illumination. The beam must remain precisely focused across vast distances. The payload must stay very small unless the beam infrastructure becomes immense. Current studies suggest that beam-driven sails may be most credible for gram-scale probes rather than human vehicles. A very small craft can tolerate brief operation-limited shielding and a narrow scientific goal, such as a fast flyby of a nearby star system. A human mission requires something entirely different. A habitat life support shielding guidance and redundancy would raise mass by many orders of magnitude. The beam power needed to accelerate such a craft to a useful fraction of the speed of light would be immense, likely requiring an energy and engineering system of extraordinary scale. The sail itself would face thermal stress material degradation and stability challenges. Even if launch were achieved, braking at the destination remains a serious difficulty unless a second beam system already exists there or some other method of deceleration can be used. The concept is physically interesting, but its usefulness may remain limited to very small probes. Fusion propulsion lies closer to familiar engineering logic. Fusion joins light atomic nuclei and releases large amounts of energy, the same general process that powers stars. Because fusion offers much greater energy density than chemical reactions, it has long seemed like a candidate for deep space travel. Concepts include pulsed systems that trigger repeated micro-explosions behind a spacecraft, and continuous systems that attempt to confine hot plasma magnetically. These ideas are not forbidden by known physics. They are, however, burdened by multiple unresolved layers. Controlled fusion for power generation on Earth remains a major scientific and engineering challenge. A propulsion system would add the need for compactness, durability, rapid pulse rates or steady confinement, efficient conversion of reaction energy into thrust, and survival of intense radiation and neutron flux inside the engine structure. Even if fusion becomes practical for stationary power, it does not automatically become practical for interstellar engines. There is also the question of fuel. Some fusion reactions require isotopes that are rare or difficult to handle. Others produce large numbers of neutrons that can damage materials, activate structures, and complicate long-term engine life. Advanced fusion pathways that produce more easily directed charged particles often demand more extreme conditions for ignition. Thus, fusion propulsion remains suspended between promise and difficulty. Observations and laboratory work indicate that fusion is real and powerful. It remains uncertain whether a fusion engine capable of driving an interstellar craft with substantial payload can be built, operated safely and sustained over the duration required. Antimatter often appears as the most extreme known energy source because matter-antimatter annihilation converts mass into energy with very high efficiency. This makes it attractive in theoretical propulsion studies, yet the gap between physical possibility and engineering reality is enormous. Antimatter production is extraordinarily inefficient with present technology, and the quantities produced are tiny. Storage requires keeping antimatter from touching ordinary matter, usually by electromagnetic confinement, which works only for charged particles and under carefully controlled conditions. Neutral antimatter is even harder to manage. Any large-scale propulsion use would require storage reliability far beyond anything yet demonstrated. In addition, the products of annihilation are not all easy to channel into directed exhaust. Some energy may emerge in forms difficult to convert efficiently into thrust-increasing heating and radiation problems. Antimatter therefore stands as an example of a concept that is physically grounded yet possibly far beyond practical reach. Some proposals go further and try to use the structure of space itself. Wormholes, if traversable, would connect distant regions through a shorter path in curved space-time. Warp concepts attempt in theory to contract space in front of a vessel and expand it behind so that the craft need not locally outrun light, even while distant points are connected more quickly than ordinary travel would allow. These ideas emerge from mathematical possibilities within general relativity, but mathematics alone does not guarantee physical realization. Known versions often require exotic matter with negative energy density, or other conditions not known to exist in usable form. Quantum field theory allows certain limited negative energy effects in special circumstances, but there is no evidence that such effects can be scaled into macroscopic transport systems. Observations support general relativity in many domains, yet they do not indicate that humanity can build traversable wormholes or warp structures. At present, such proposals remain speculative and unsupported as engineering paths. Even more modest exotic ideas face a recurring pattern. A concept may reduce one known difficulty only by introducing another. A sail avoids carrying propellant, but demands giant beam systems and struggles to break. Fusion offers better energy density, but requires engine conditions not yet mastered. Antimatter offers even greater density but faces production and containment barriers. Space-time engineering bypasses conventional motion only by depending on physics not yet shown to be available in the needed form. This pattern does not prove permanent impossibility, but it does reveal why advanced propulsion should not be confused with simple future inevitability. The phrase advanced can hide the fact that multiple independent miracles of engineering materials, science, and perhaps physics would need to align. Another important distinction lies between robotic and human missions. Many advanced propulsion concepts become more plausible. When the payload is tiny, the mission is one way, and arrival is reduced to data collection during a rapid pass. Humanity, however, is not a gram-scale payload. A human vehicle must preserve life, not merely carry instruments. It must survive failure modes, not merely maximize speed. It must provide radiation protection, thermal control, and the means for repair. These requirements push mass upward and narrow design tolerance. A propulsion concept that appears promising for a miniature probe may become far less useful for a crewed expedition. Thus, the question of interstellar travel for humanity is stricter than the question of whether any object at all might someday cross between stars. Scientific caution is therefore important in this region. It is reasonable to say that some advanced propulsion concepts are consistent with known physical principles in limited ways. It is also reasonable to say that no such concept has yet demonstrated a credible pathway to transporting human beings between stars. There is ongoing research into sails, compact high-energy systems, fusion antimatter physics, and the deep structure of relativity. These fields matter. They expand knowledge. Yet present evidence does not justify the calm assumption that one of them will eventually dissolve the interstellar barrier. Observations indicate possibilities at the margins. It remains uncertain whether any of those possibilities can mature into civilization-scale transport. This inward step therefore removes another layer of comfort. When conventional rockets fail, it is tempting to believe that the answer must lie in something more exotic, waiting just beyond the horizon. The record of physics advises more restraint. Nature does not guarantee a hidden door simply because the known door is narrow. It may be that some advanced method will one day send instruments to nearby stars. It may also be that every currently imagined method remains trapped by some combination of energy, demand, material, weakness, thermal stress, beam precision radiation, or unresolved physics. For humanity, that distinction matters greatly. In this region, interstellar travel may be impossible not because there are no ideas, but because the ideas that survive contact with known science may still fail contact with full reality. The farther propulsion moves from present machines, the more it depends on conditions that must be not only conceivable but buildable, stable, and scalable. Between stars, plausibility in principle may never become practicality in fact. If a spacecraft could somehow reach a very high fraction of the speed of light, the meaning of travel time would become less simple than ordinary language suggests. In everyday life, time appears to flow in the same way for all nearby observers. Two clocks placed side by side and treated similarly remain in agreement. A traveller leaving one city and entering another does not return to find that centuries have passed for those who stayed behind. At low speeds, such differences are too small to matter. At relativistic speed, they become physically real. The time measured aboard a moving craft can differ from the time measured by observers who remain on Earth. This effect, known as time dilation, belongs not to speculation but to the tested framework of special relativity. Experiments over many decades support this description. Fast-moving unstable particles survive longer than they would at rest, because less time passes for them in their own frame. Highly precise clocks flown on aircraft or placed in satellites show measurable differences from clocks on Earth, after corrections for both motion and gravity are included. Global navigation systems must account for relativistic effects in order to remain accurate. The science is therefore not in doubt in its broad outline. Motion at high speed changes the relation between time and distance. For interstellar travel, this means that the duration felt by travellers need not match the duration recorded by those who watch the mission from Earth. At first, this seems to soften the difficulty of reaching other stars. If time passes more slowly aboard a fast-moving ship, then a journey that takes decades or longer in the Earth frame may feel shorter to those inside the vehicle. In principle, this is true. A sufficiently fast craft could carry travellers to a distant star within a span of subjective time shorter than the corresponding duration on Earth. Yet this relief is narrower than it first appears. Time dilation does not make the journey easy. It does not reduce the energy required to achieve the speed. It does not remove the hazards of acceleration shielding isolation or deceleration. It changes the distribution of elapsed time between different observers, but it does not erase the underlying physical burden of the mission. There is also the matter of acceleration itself. A spacecraft does not begin its voyage already moving at relativistic speed. It must increase its speed gradually or in stages, and the occupants must endure whatever acceleration is chosen. Human bodies are adapted to the steady pull of gravity near Earth's surface. They can tolerate changes in acceleration for limited periods, but there are practical limits. A short, intense acceleration may damage the body or render a person unconscious. A lower acceleration maintained over a longer period is gentler, yet it lengthens the journey phase before cruise speed is reached. Thus, the human experience of time in transit depends not only on cruise velocity, but also on the chosen acceleration profile and the biological tolerances of the travellers. If a mission attempted to maintain a comfortable acceleration for a long period, the ship could in theory build up very high speed over time, while also providing an artificial sense of weight for the crew. This idea appears attractive because it seems to address both motion and habitability. Yet it carries severe demands. Sustained acceleration for months or years requires an enormous and steady expenditure of energy. The propulsion system must operate reliably over long durations without catastrophic failure. It must then reverse the process and provide corresponding deceleration as the destination approaches. The elegant symmetry of constant acceleration is therefore constrained by the same realities that govern propulsion and energy. It is not a free gift from relativity. It is a demanding mission architecture. Even if these demands were somehow met, the human meaning of time would become complicated in ways that are not merely physical but civilizational. A traveller might experience a journey of a few years or decades while a much longer span passes on Earth. Friends, institutions, languages, governments and cultures may change profoundly during the absence. A mission that preserves subjective life aboard the vessel may still sever continuity with the society that launched it. This is an important distinction. Relativity can in principle compress the traveller's own experience of duration, but it does so at the cost of widening their temporal separation from home. The ship becomes not only distant in space but displaced in history. This separation has a quiet emotional weight. Human life is not measured by biology alone. It is measured by relationship, memory, obligation, and belonging. A mission that returns after many decades or centuries of Earth time may return to a civilization transformed beyond recognition, if it returns at all. For a one-way mission, the gap may be even more final. Relativistic travel therefore raises a question deeper than endurance. It asks whether a journey remains human in an ordinary sense when the travellers are cut loose from the temporal world that formed them. The body may survive the transit. The self may survive it in another sense. Yet the web of life to which that self belongs may not. Time dilation also does not rescue missions that cannot achieve extreme speeds. The effect becomes significant only as velocity rises close to the speed of light. At lower but still impressive speeds, the difference in elapsed time is real but modest. A craft moving at 1/10 of the speed of light does not enjoy dramatic relief from subjective duration. To obtain strong time dilation, the mission must enter the same region of speed, where energy costs and shielding demands become especially severe. Once again, one apparent solution stands close to another difficulty. The universe permits the effect, but only under conditions that may be too costly for humanity to realize. General relativity adds another layer, though less central for most interstellar mission concepts. Gravity also affects the passage of time. Clocks deeper in a gravitational well run differently from clocks farther out. This effect is well established and measured. For travel between stars, however, the dominant time difference during the voyage would usually come from speed rather than from gravitational extremes, unless the mission passed very near unusually massive objects. The main lesson remains the same. Time is not absolute in the simple sense assumed by ordinary life. It is part of the structure shaped by motion and gravity. Interstellar travel does not merely take place in time, it rearranges the experience of time itself. There is a temptation to speak of relativistic travel as a path around mortality. That would be misleading. A traveller may age more slowly relative to those left behind, but the traveller still ages according to the proper time experienced aboard the craft. Biology does not become timeless. Supplies do not become infinite. Equipment does not cease to wear. Psychological duration still matters. A voyage of several subjective years remains several years of living in confinement, depending on machines' routines and social stability. Relativity changes comparison between observers. It does not abolish the lived reality of a closed journey. This matters because interstellar travel for humanity is not only a problem of reaching a coordinate in space, it is a problem of carrying persons through time in a form that preserves life, meaning, and function. Relativity offers an austere kind of mercy. It says that under high-speed motion the travellers need not endure the full external duration measured by distant observers. But the same physics also says that no information object or rescue outruns light, and that the price of entering the regime where time dilation becomes powerful is extremely high. The benefit arrives entangled with cost. In this region, the barrier to interstellar travel becomes more intimate. Earlier difficulties concern distance, medium speed, and energy. Here the problem reaches the human calendar. Time itself ceases to be a neutral background and becomes part of the mission's burden. A journey may be shortened for those aboard only by deepening the gap between them and Earth. A ship may cross to another star within the lifetime of its crew only by leaving behind the time of everyone else. For a species bound not only by flesh but by generations, memory, and mutual presence, This is no small complication. It suggests that even if the machinery of flight could be built, the human meaning of arrival might already be slipping away during the voyage. Interstellar travel may therefore be impossible for humanity in a sense more subtle than mechanical failure. It may demand speed so high that time itself begins to separate travellers from the civilization that sends them, while the cost of achieving those speeds remains almost beyond reach. In that calm tension between physics and human continuity, the journey grows stranger and harder. The stars remain ahead, but the shared time that makes a voyage recognizably human begins to thin. Inside any interstellar mission concept beyond the mathematics of trajectory and the abstractions of speed, there must exist a real physical vessel. It is not enough for a path to be calculable or for an engine to be theoretically possible. The spacecraft itself must remain whole across years, decades, or longer, while moving through a hostile environment with little chance of outside repair. This requirement draws attention inward from cosmic distance and relativistic time toward the material shell that must bear all burdens at once. In this region, interstellar travel becomes a question of whether any machine built by humanity can preserve its own integrity long enough to complete such a journey. A spacecraft on an interstellar route would face no atmosphere in the ordinary sense, yet its environment would still be active and wearing. The vacuum of space prevents convection, which means heat cannot be shed in the same easy way it is lost to moving air or water on Earth. At the same time, the spacecraft would generate its own heat through electronics life support, computing propulsion systems and internal circulation. If the vehicle travels at high speed, particle impacts and radiation exposure may add further heating in exposed areas. The only long-term way to reject this heat is through radiation, by emitting infrared energy from surfaces or radiators into space. This sounds simple in principle, but in practice it is limiting. Radiators must have sufficient area-suitable orientation and structural durability. They add mass-create vulnerable exposed surfaces and must continue to function over very long durations without fouling cracking or losing emissivity. Thermal control is not only about removing excess heat, it is also about distributing heat and preventing dangerous cold. In deep space, shaded surfaces can drop to very low temperatures, while illuminated or internally heated regions may remain much warmer. This can create thermal gradients across the structure. Materials expand and contract as temperature changes, and repeated cycles of heating and cooling can introduce fatigue over time. Seals may stiffen or fail. Joints may loosen. Electronics may drift out of their ideal operating range. Lubricants may degrade or behave unpredictably. On short missions, such problems can often be reduced by careful design margins. On interstellar missions where no immediate maintenance crew waits nearby and no replacement launch can arrive, the same problems must be contained not for months, but for spans that approach the lifetime of the vehicle itself. Structural fatigue becomes especially important in this context. A spacecraft is often imagined as static once it leaves its launch system, but in reality it experiences continuous small stresses. Rotating systems, vibration from onboard machinery flexing under thrust, thermal cycling, micrometeoroid, or dust impacts, and the slow effects of radiation all contribute to wear. Metals can accumulate microscopic cracks. Composite materials can delaminate. Coatings can erode. Protective layers can become brittle. In the interstellar medium, even tiny impacts repeated over time may roughen surfaces, weaken leading edges, and alter optical properties that sensors or radiators depend on. The danger is not necessarily one dramatic failure alone. It is the gradual thinning of reliability, the quiet conversion of safety margins into uncertainty. Radiation deepens this concern. High-energy particles can damage electronics through single-event effects, where one particle striking a microelectronic component causes a bit flip, a false command, or a temporary malfunction. Over longer periods, radiation can also cause cumulative degradation in semiconductors, solar devices, sensors, cables, and insulation. Modern electronics, though powerful, often depend on very small structures that can be especially sensitive to energetic particles. Radiation hardening can improve resilience, but it may reduce performance, increase mass, or raise power demands. Redundancy helps, yet redundancy itself is not infinite. A mission lasting decades cannot simply assume that backup systems will remain pristine forever. Each backup is also aging in the same environment. Shielding, therefore, becomes one of the spacecraft's defining architectural features. Yet shielding is never free. A thick physical barrier can block or slow many particles, but it adds mass, and mass affect propulsion and structural design. Different types of radiation demand different protective strategies. A shield effective against one hazard may be less effective against another. Very energetic cosmic rays can pass through substantial material and produce secondary radiation as they interact with shielding. Dust protection may require strong leading surfaces, while radiation protection may favor different materials and internal arrangement. Thermal requirements may conflict with both. The spacecraft becomes a compromise machine, its geometry shaped by the fact that no single material or layout solves all environmental problems at once. Pressure containment adds another layer if humans are aboard. A crewed vehicle must keep air inside and vacuum outside for the full duration of the mission. Even small leaks can become serious over time. Pressure hulls must resist not only immediate rupture but slow degradation. Windows, if any exist, are structural weaknesses compared with solid walls. Hatches, seals, ducts, and ports all create possible failure points. Designers can reduce risk by minimizing openings and simplifying the hull, but habitability often pushes in the opposite direction. Human beings require access, storage, sanitation, movement, and functional separation of systems. The more complex the interior becomes, the more interfaces and potential weaknesses appear. Mechanical simplicity is often praised in reliable engineering, and with good reason. Fewer moving parts usually mean fewer opportunities for failure. Yet interstellar spacecraft, especially those meant to support life, may need many moving systems: pumps, valves, fans, gyroscopes, robotic arms, recycling equipment, repair tools, guidance mechanisms, and perhaps rotating sections, if artificial gravity is attempted through spin. Each of these systems offers benefits, but each also adds bearings, joints, power lines, sensors, and control loops. Over long durations, even very low annual failure rates become significant. A device that is highly reliable over a few years may still be likely to fail over a few decades. Reliability must therefore be thought of not as a static label, but as a probability spread across time, and interstellar time is merciless to such probabilities. Autonomous repair may seem like the answer. A spacecraft could in principle carry spare parts, diagnostic systems, and robotic maintenance tools. Additive manufacturing, sometimes called three-dimensional printing, may allow some components to be made on board from stored raw material. Software could detect degradation early and shift loads away from failing systems. These ideas are promising, and some already support present-day space operations in modest ways. Still, they do not abolish the problem. Spare parts increase mass. Raw material is finite. Repair machines themselves can fail. Not every part can be fabricated easily in transit, especially highly specialized electronics or complex composites. Some failures may arise from causes too subtle to diagnose in time. An interstellar spacecraft may become a workshop as well as a vehicle, but a workshop is not the same thing as a self-sustaining industrial base. Navigation and control systems must also endure. A ship crossing light years cannot drift carelessly. Even a minute error in attitude or trajectory can grow into a large miss over time. Star trackers, inertial sensors control thrusters, reaction wheels and computing systems must keep functioning with extraordinary stability. Optical systems may lose clarity. Calibration may drift. Radiation may introduce faults. Dust impacts may pit exposed surfaces. A mission can include redundancy and cross-checking, but it cannot assume that perfect reference and correction will remain effortless over many years. A slight failure in guidance may not become obvious until correction is difficult or impossible. The spacecraft environment is therefore not a neutral container around the voyage. It is an active and fragile middle layer between harsh space outside and vulnerable life, or instruments within. Present-day spacecraft already show how hard long-duration reliability can be even for robotic missions within the solar system and under strong support from Earth. Some perform brilliantly for far longer than expected, which demonstrates the skill of their designers. Yet even these successes occur over distances and timescales far smaller than those demanded by interstellar travel, and they often depend on simplified mission goals, passive endurance and acceptance of gradual capability loss. A human interstellar vehicle would require a much higher standard. It could not merely survive in reduced form, it would need to remain habitable, accurate and repairable. This is why the possibility of impossibility sharpens further here. Even if propulsion energy and speed could somehow be managed, the machine carrying the journey may still fail under the accumulated strain of duration. Interstellar travel asks for a spacecraft that functions not only as a vehicle, but as a sealed environment, a thermal system, a radiation shelter, a repair platform, a navigation instrument, and perhaps a home. Every one of those roles wears at the others. More shielding means more mass. More redundancy means more complexity. More habitability means more systems to maintain. The vessel must be strong yet light, repairable yet simple, protective yet efficient. In the quiet logic of engineering, these demands may become too many at once. A spacecraft can survive short missions by accepting fragility and replacing what breaks later. It can survive some long missions by narrowing its purpose and reducing its needs. Interstellar travel for humanity allows neither freedom. The ship must endure without easy rescue, without resupply, and without the forgiving timescale of local operations. If no machine can remain sufficiently whole under those conditions, then the journey fails not in the stars, not in the equations, but in the shell that tries to carry human life across the dark. Within the protective shell of a long-range spacecraft's survival depends on a quieter system than the engines or shields. A vehicle may cross distance only if it can also preserve the daily conditions of life. Air must remain breathable. Water must remain available and clean. Food must be produced, stored, or carefully rationed. Waste must be removed or transformed. Microbes must be managed. Materials must cycle through use and recovery without drifting steadily toward contamination or depletion. These requirements define life support, and on an interstellar mission, they become more than a technical subsystem. They become an enclosed ecology, a living balance that must hold steady across spans far longer than most machines are ever asked to operate. On Earth, life support is so broad and stable that it often goes unnoticed. The atmosphere dilutes waste gases and supplies oxygen through vast planetary cycles involving plants, oceans, soils, and chemistry. Water moves through clouds, rivers groundwater ice, and living tissue replenished by sunlight and gravity. Food webs draw on a biosphere of enormous complexity and resilience. Human settlements do not usually recycle every molecule internally. They depend on a planet-sized background system. Spaceflight removes that background. In orbit or on deep space missions, every litre of water, every unit of oxygen, and every gram of food must be tracked with care, because the surrounding environment offers almost nothing useful without major processing. Interstellar travel intensifies this reality. Resupply is not delayed, it is absent. A closed life support system aims to recycle essential materials so that a crew can survive without constant external input. Carbon dioxide exhaled by the crew must be removed from the air and ideally converted back into useful forms. Water from breath, sweat, urine, washing, and other sources must be recovered and purified. Solid waste must be stored, processed, or broken down. Trace contaminants released by plastics, cleaning products, machinery, microbes, and human metabolism must be kept below harmful levels. This is already difficult on missions lasting months. Over years or decades, the challenge becomes deeper because small inefficiencies accumulate. A system that loses only a tiny fraction of the water or air each day may still become unsustainable over a long enough journey. This cumulative problem is one of the main reasons life support is not simply a plumbing issue. It is a problem of long-term balance. Filters clog, seals wear, catalysts degrade, pumps fail, microbial films form in pipes and tanks, sensors drift, chemical absorbers become saturated. Even if each individual loss is small, a closed environment gives those losses nowhere to disappear. They remain inside the mission as growing disorder. What Earth resolves through vast environmental buffering, a spacecraft must resolve with limited mass, limited energy, and limited room for redundancy. Water recycling is often treated as one of the more tractable parts of the problem, because water can be purified through established physical and chemical methods. Present space systems already reclaim a significant fraction of wastewater for reuse, yet very high recovery rates sustained over interstellar durations are another matter. A system can perform well for years and still not meet the demands of decades if replacement parts, maintenance effort, and material losses are too great. Purity standards also matter. Water need not be perfectly pure in an abstract sense, but harmful compounds must be controlled at very low levels. In a closed habitat, impurities can recirculate in subtle ways. A trace contaminant that escapes notice at first may slowly build until it affects health or system function. Air recycling brings its own complications. Oxygen can be stored for limited missions, but for a very long voyage, it is far more efficient to regenerate it from water or from biological systems. Carbon dioxide removal is essential because even moderate accumulation can impair cognition, cause discomfort, and harm health. Space habitats have already shown that carbon dioxide control can be more difficult than it first appears even over relatively short durations. In a long mission, the atmosphere is not just a gas mixture, it is a managed chemical environment. Humidity, trace gases, pressure, and circulation all influence comfort, health, fire risk, and microbial growth. If airflow becomes uneven, pockets of stale air can form. If filtration falters, tiny particles may accumulate. If a conversion system runs slightly off target, imbalance can grow over time. Food introduces an even more demanding dimension. Stored food is possible for limited missions, but food degrades. Vitamins break down, texture changes, packaging ages. Over very long periods, stored diets become difficult to preserve in full nutritional quality. This is one reason many long-duration concepts consider growing food on board. Biological food production, however, is not simple agriculture moved into space. Plants require light water nutrients, temperature control and protection from disease. Their growth cycles must align with human dietary needs. Pollination, harvesting and processing must be managed. Waste biomass must be composted or otherwise reintegrated into the system. A biological food loop can also contribute to oxygen production and carbon dioxide uptake, which is attractive. Yet this same interdependence makes the habitat more complex. If crops fail, multiple support functions may be impaired at once. Microbes complicate all closed systems. Human beings do not travel alone. Their bodies carry vast communities of bacteria, fungi, and other microorganisms that are usually harmless or beneficial in normal balance. In a sealed habitat, microbial populations can shift in response to humidity surfaces, cleaning routines, radiation stress, and altered immune function. Some microbes form resistant films on equipment. Others may threaten stored food or crew health. On Earth, buildings can often be cleaned, emptied, renovated, or supplied anew. An interstellar spacecraft cannot depend on such resets. It must manage a living microbial environment continuously, without allowing that environment to drift into instability. Ecology in a closed habitat is therefore not simply a matter of keeping people alive by mechanical means. It becomes an effort to sustain a small artificial biosphere. The narrower and more closed the system becomes, the more every component interacts with every other component. Water chemistry affects crops. Crops affect air composition. Waste processing affects microbial balance. Power availability affects lighting and temperature, which affect food production and health. The crew themselves alter the system through metabolism, labor, error, and illness. Even human mood matters, because demoralized or exhausted crew may neglect maintenance or respond poorly to subtle warning signs. Experiments on closed ecosystems on Earth have shown both promise and difficulty. They demonstrate that partial recycling and tightly managed ecological loops are possible. They also reveal how hard it is to predict every interaction in advance. Trace gases can accumulate unexpectedly. Soil chemistry can shift. Pest populations can rise. Human labor demands can become larger than expected. Small imbalances may take time to appear and then prove difficult to correct. These lessons are valuable because they show that the problem is not a lack of imagination. It is the complexity of life itself when compressed into a bounded volume with minimal room for error. For a human interstellar mission, life support must do more than function. It must function continuously, predictably, and repairably through a duration that may exceed the design life of most industrial systems ever built. It must tolerate illness, equipment, breakdown, crop failure, contamination events, and shifts in crew size or need. It must do this while using limited energy and mass inside a spacecraft already burdened by shielding structure and propulsion. The margin for failure is narrow because no nearby world, no resupply mission, and no broad planetary ecology waits outside the hull. This is where the question of impossibility becomes biological as well as technical. A machine can sometimes continue in degraded form. Human life support cannot degrade very far before the mission becomes untenable. The air cannot be almost safe. The water cannot be mostly clean. The food system cannot work only in favorable months. A closed habitat carrying people across interstellar space must perform with a steadiness that approaches the quiet reliability of Earth, but without Earth-scale diversity or resilience. Interstellar travel may therefore be impossible for humanity, not only because reaching another star is hard, but because remaining alive in transit may require a degree of ecological control that human engineering has not yet demonstrated and may never fully master in a sealed, artificial world. The outer challenge of distance leads inward to a more intimate boundary. A journey between stars is also a long experiment in whether life can be folded into machinery without losing the stability that life on Earth receives freely from a whole planet. If that folding cannot be made durable enough, then the spacecraft becomes not a bridge between stars, but a fragile island too isolated to sustain its own living balance for the time the voyage demands. Inside the closed habitat of a long interstellar voyage, the human body becomes one more system under strain. Though unlike pumps, filters and tanks, it cannot simply be replaced by a spare part when its balance begins to drift. Human physiology forms over millions of years under the steady pull of gravity inside a thick atmosphere under the shielding of a planetary magnetic field, within cycles of day and night weather and season movement and rest. Space removes or weakens many of those conditions at once. A short mission can tolerate this disruption for a limited time. A journey lasting many years or decades would ask the body to persist far outside the environment in which it evolved. In this region, interstellar travel becomes a question not of whether a ship can carry human beings, but of whether human beings remain healthy enough in transit to arrive as functioning people at all. One of the clearest bodily changes in space comes from microgravity, the condition of prolonged weightlessness experienced during orbital flight, and likely during long cruise phases, unless artificial gravity is created. In the absence of regular loading, bones begin to lose mineral density. Muscles, especially those that maintain posture and support, walking on Earth, begin to weaken and shrink. The cardiovascular system changes as fluids redistribute upward through the body, altering blood volume, heart workload and vascular control. Balance and orientation can also be affected because the inner ear no longer receives gravity in the familiar way. These effects are not speculative. They are observed repeatedly in astronauts during and after missions in orbit. Exercise, careful nutrition and medical monitoring can reduce some of the damage, but they do not eliminate it completely. Bone loss is especially important for interstellar thinking because it can become cumulative. On Earth, bones constantly remodel themselves, responding to mechanical stress. Without sufficient stress, the balance shifts and bones lose density. This increases the risk of fracture and may also contribute to kidney stone formation as released minerals circulate and are excreted. Present space crews exercise for long periods each day to preserve bone and muscle, using specially designed equipment that creates resistance in weightlessness. Even so, some loss still occurs. A mission much longer than current human flights would place greater demands on both equipment and compliance. The body must not only survive during cruise, it must remain capable of useful work during emergencies and capable of functioning in gravity again if the crew arrives at a planetary destination. Muscle loss follows a similar pattern. In everyday life on Earth, standing, walking, lifting, and simple movement constantly train the body. In weightlessness, many of those demands vanish. Muscles used for posture and locomotion can weaken rapidly, if not deliberately exercised. Weak muscles reduce endurance, strength, coordination, and resilience. This affects not only comfort, but mission safety. A crew facing repairs, medical emergencies, or a difficult arrival cannot depend on bodies weakened by years of underloading. Artificial gravity through rotation is often proposed as a remedy because it could restore a more Earth-like mechanical environment. Yet creating artificial gravity introduces its own engineering and human factor complications. Rotating structures add mass and complexity. The rotation rate and radius must be chosen carefully to reduce disorientation and uneven forces. Observations indicate that artificial gravity may help, but it remains uncertain how effective partial or rotating gravity would be across very long durations. Radiation presents an even deeper biological concern. Outside Earth's atmosphere and magnetic field, the body is exposed to a harsher particle environment. Galactic cosmic rays include very energetic particles capable of penetrating shielding and tissue. Solar energetic particle events can also deliver substantial radiation over short periods, depending on solar activity and mission timing. Radiation can damage DNA directly or indirectly through chemical processes inside cells. The body can repair some damage, but not perfectly. Accumulated exposure raises the risk of cancer, cataracts, cardiovascular effects, and possible changes to the nervous system. In a mission lasting many years, the total dose could become substantial even with shielding, especially because some high-energy particles are difficult to block completely. The nervous system is a particular concern because human performance depends on cognition as much as on raw survival. Studies of radiation effects in animals and indirect evidence from human exposure suggest possible impacts on memory, attention, and neural health at sufficient doses, though the full picture remains uncertain for the specific mixture of space radiation encountered during long missions. This uncertainty is itself serious. A crude interstellar voyage would rely on sustained judgment, emotional regulation, technical skill, and social coordination. Any agent that threatens not merely lifespan but the quality of thought becomes a mission-wide hazard. Shielding can reduce some exposures, but thick shielding adds mass, and some very energetic particles can produce secondary radiation when they strike protective material. The body therefore travels in a region where protection is possible but incomplete. The immune system may also change in prolonged spaceflight. Observations from astronauts suggest that immune responses can be altered by the combined effects of weightlessness, radiation, stress, confinement, altered sleep, and other mission factors. Latent viruses may reactivate. Wound healing may change. Inflammation may shift. None of this guarantees catastrophic illness, but it suggests that long missions may make the body less predictable in its response to infection, injury, and stress. In a sealed habitat with a limited medical inventory, limited specialist care, and delayed communication, even a modest decline in immune stability can matter. A disease that would be manageable on Earth may become more dangerous when evacuation is impossible and treatment options are narrow. Sleep and circadian rhythm form another bodily layer. On Earth, the body follows roughly 24-hour cycles linked to light, temperature, activity, and social routine. Spacecraft can impose artificial lighting schedules, but maintaining healthy sleep across years is not trivial. Noise confinement, stress work cycles, and the absence of natural environmental cues can all affect rest. Poor sleep then influences mood, attention, metabolism, and immune function. Over time, repeated sleep disruption can become not a minor inconvenience, but a chronic weakening of resilience. An interstellar mission would need to manage light exposure workload and psychological routine with great care, because biological time inside the body does not stop mattering simply because the stars outside are far away. Reproduction and development introduce further uncertainty, though not every mission concept depends on them. If a voyage spans more than one generation, or if conception during flight is possible, then the effects of radiation, altered gravity, and closed ecological conditions on fertility, pregnancy, fetal development, and childhood growth become deeply relevant. Current knowledge in these areas is limited. Mammalian biology depends on finely regulated developmental processes, and it remains uncertain how well these would proceed in prolonged weightlessness or under chronic space radiation. Even if reproduction were intentionally avoided, the mere fact that these questions remain unresolved shows how incomplete present understanding is when human life is imagined beyond short missions. Medical care on board can reduce risk but cannot turn the spacecraft into a full hospital. Medicines degrade over time. Equipment has limits. Surgical capability and weightlessness is difficult. Diagnostic tools may be constrained by mass power and maintenance needs. A highly trained crew can prepare for many emergencies, yet not for all of them. Chronic illness, trauma, cancer, degenerative changes, and subtle neurological or psychological decline all become harder to address when there is no rapid return. The body is not a passive payload. It is an aging, vulnerable organism that can develop new failure modes as the mission unfolds. Age itself must be considered calmly. Many interstellar mission concepts require durations measured in decades, unless extraordinary propulsion is achieved. A crew beginning in young adulthood may arrive in middle age or later. Even if time dilation reduces the subjective span in some designs, current realistic mission concepts do not remove aging aboard the ship. Human bodies accumulate wear. Recovery slows. Disease risk changes. A mission profile that seems possible for a strong adult at departure may become much less forgiving later. The body that leaves Earth is not the same body that would face arrival. All of this suggests that the human organism may be less portable than the human mind prefers to believe. Machines can be redesigned for vacuum and radiation. Bodies cannot be redesigned so easily. They carry ancient adaptations to one world, one gravity level, one atmospheric chemistry, one protective sky. Space travel already reveals this through measurable physiological change on missions far shorter than those required for the stars. Interstellar travel would magnify the exposure, extend the duration, and narrow the chance of rescue. The body would have to endure weightlessness or engineered gravity radiation confinement, altered sleep, limited medicine, persistent stress, and the slow advance of age, all while remaining capable of meaningful action. Interstellar travel may therefore be impossible for humanity, not only because engines may fail or habitats may drift out of balance, but because the human body itself may not remain stable enough through the passage. A voyage between stars does not transport a neutral unit of life. It transports a planetary animal whose tissues, hormones, bones, microbes and rhythms are deeply shaped by Earth. If those inherited dependencies cannot be supported well enough in transit, then the barrier to the stars lies not only in the distance outside the ship, but in the biology carried within it. Beyond the engineering of the vessel and beyond the limits of the body lies a quieter and less measurable challenge. Human beings do not travel as isolated organisms alone. They travel as social minds shaped by memory, language, expectation, routine, conflict, affection, status, and shared purpose. A long interstellar voyage would place these social and psychological structures inside a sealed environment, with little novelty, little privacy, and almost no possibility of departure. In this region, the question is no longer whether the ship can move or whether the body can endure. It is whether a small human community can remain mentally stable, cooperative, and meaningfully connected to its own mission across a span that may outlast familiar social forms. Shorter missions in space already show that confinement matters. Astronauts live under strict schedules, limited room, artificial light, repeated routines, and constant awareness of danger. Even with careful selection and training, interpersonal strain can arise. Irritation, fatigue, isolation, homesickness, sleep disruption, and the subtle wear of repeated proximity are all documented concerns. Earth-based simulations of isolation, such as polar stations, underwater habitats, and sealed research environments, point in the same direction. People can adapt impressively to confinement, but adaptation is not effortless and not always stable. Group mood can shift over time. Small tensions can harden into persistent conflict. Leadership can become brittle. Motivation can weaken. A mission lasting years may remain difficult. A mission lasting decades or longer moves into a more uncertain social territory. The first issue is monotony. Human attention and emotional balance are influenced by variation in place, season, weather. spontaneous encounter, and changing physical surroundings. A spacecraft offers only limited variety. Its walls, sounds, corridors, and systems may become deeply familiar, then oppressive in their familiarity. Even carefully designed interiors may not prevent the slow, flattening of experience that comes when the external world remains unreachable and largely unchanged. Screens can display landscapes, music can vary, schedules can rotate, but representation is not the same as open reality. Over long durations, monotony may not produce immediate crisis. Instead, it may erode vitality, curiosity, and patience, leaving the crew more vulnerable to depression, apathy, and interpersonal strain. Privacy is another fragile necessity. Human beings usually regulate stress by moving between social contact and solitude. In a sealed spacecraft, private space may be very limited. Even when separate sleeping quarters exist, sound vibration schedules and awareness of others can intrude. A person who cannot withdraw adequately may become emotionally exhausted. At the same time, too much withdrawal can weaken group cohesion and foster alienation. Mission design must therefore balance privacy with cooperation, but balance is difficult when volume and mass are limited. On Earth, communities can disperse after conflict and reconnect later. In interstellar transit, the same people remain together because there is nowhere else to go. Purpose is equally important. Many hardships become bearable when their meaning is clear and collectively accepted. A spacecraft crew may begin with a strong sense of mission discipline and commitment. Over time, however, that clarity may blur, especially if the destination remains abstract and the journey consumes most of a lifetime. Immediate tasks may fill the days, but long-term motivation is harder to preserve when success lies far beyond present experience. Some crew members may continue to identify deeply with the mission's goal. Others may come to value only local survival, daily comfort, or private relationships. If the shared narrative weakens the mission, ceases to be a unified undertaking and becomes merely a prolonged coexistence inside machinery, authority and governance would therefore matter profoundly. Every closed community develops rules, expectations, and power relations. On a short mission, a command structure can be clear, reinforced by training and close contact with Earth-based control. Over a very long voyage, especially one with great communication delay, authority must become largely internal. The crew or their descendants would need systems for decision-making, conflict resolution, discipline, and adaptation. No system is free of risk. A rigid hierarchy may preserve order at first, but foster resentment, conceal error, or suppress needed change. A highly flexible system may encourage participation, but struggle during crisis. Political life, even in a small habitat, does not vanish, because the setting is technological. It intensifies because the stakes of every disagreement are enclosed. Trust becomes one of the mission's most valuable and delicate resources. A crew must trust the competence and intentions of others. They must trust that maintenance is performed honestly, that medical judgments are sound, that resources are shared fairly, and that leadership decisions are not arbitrary. Once trust begins to fail, the consequences can spread through every layer of life. Ordinary misunderstandings may acquire moral weight. Technical errors may be interpreted as personal betrayal. Factions may form around different interpretations of risk, fairness, or purpose. In an environment where every person depends on every other for survival, distrust is not merely unpleasant. It is destabilizing at the deepest practical level. The possibility of multi-generational travel sharpens these concerns further. If a voyage takes longer than one human lifetime, then later, inhabitants would be born into the mission rather than choosing it. This changes the ethical and social structure completely. The founding generation may consent to hardship in pursuit of a distant star. Their descendants do not consent to be born aboard a ship inside a project defined before their existence. They may inherit duties, risks, and confinement without having endorsed the mission that imposes them. Education, culture, and social norms could encourage loyalty to the voyage, but it remains uncertain whether such loyalty could remain stable across generations. A later generation may question why it must preserve the goals of ancestors rather than redefine its own future within the ship itself. This issue is not merely philosophical. It affects daily governance, labour distribution, and legitimacy. A multi-generational vessel would need children schooling social roles and eventually adults who maintain systems they did not design for a destination they have never seen. The ship might become less like a mission and more like a miniature society. Such a society would still be technically bound to the voyage, but its members might not experience themselves primarily as travellers. They might experience themselves as residents of a closed world whose first obligation is internal continuity, not arrival. In that case, every system of education and culture becomes part of propulsion in a broad sense, because the mission survives only if meaning survives with it. Psychological diversity complicates the picture in both good and difficult ways. Different personalities contribute resilience, creativity, and a wider range of problem-solving approaches. At the same time, diversity of temperament can increase friction under confinement. Some individuals need more solitude, others more social reassurance. Some respond to stress with rigidity, others with improvisation. Some need stable routine, others need novelty. A group selected only for harmony may lack adaptability. A group selected only for competence may lack cohesion. Over long periods, people also change. Grief, illness, disappointment, aging, and shifting relationships reshape personality expression. A crew that begins compatible may not remain so indefinitely. The absence of Earth as a living background intensifies every inner difficulty. Earth is not only a home remembered emotionally, it is a source of continual renewal through communication, culture, landscape, and the knowledge that return remains conceptually possible. On an interstellar voyage, especially after great distance has accumulated, Earth becomes less a place in active relationship and more a historical origin. Messages, if they arrive at all, are delayed by years. News becomes archival by the time it is received. Shared events dissolve into separate timelines. This separation may produce loneliness of a distinctive kind, not merely the lack of company, but the loss of simultaneous belonging to a larger human world. Ritual art, recreation, and storytelling would likely become essential forms of psychological maintenance. They can structure time, preserve meaning, reduce stress, and support identity. Yet even these supports depend on social energy and cultural continuity. A tired or fragmented community may struggle to sustain them. The mission would need not only engineers and physicians, but also stable forms of celebration, mourning, conflict repair, and collective memory. These are not luxuries. They are part of what keeps human beings from becoming merely biological occupants of a machine. Scientific knowledge can describe parts of this region, but not all of it with confidence. Psychology, psychiatry, sociology, and space medicine offer evidence from isolation studies, submarines, polar stations, long-duration simulations, and orbital missions. These sources indicate that humans can endure confinement with training and support. They also indicate persistent risks of conflict depression, sleep disruption, stress-related decline, and social fracture. It remains uncertain how those risks scale across decades, across great communication delays, or across generations born in transit. No human society has yet lived for such duration inside a moving sealed spacecraft. The absence of experience here is itself a warning. Interstellar travel may therefore be impossible for humanity not only because space is cold, distant, and energetic, but because human community may not remain coherent enough in captivity to carry the mission through. A spacecraft can be designed as a machine. A long voyage must also function as a culture. If that culture loses trust, meaning justice, or psychological balance, then the journey can fail while the hull remains intact and the engines remain silent but ready. The deeper enclosure is not metal around bodies. It is time around minds pressing year after year on the social bonds that make a group something more than a set of survivors sharing air. As the spacecraft moves farther from the sun and deeper into the space between stars, another form of distance becomes unavoidable. Separation is no longer measured only in kilometers or in years of travel. It is measured in the slow movement of information itself. Messages do not cross the gulf instantly. They move at the speed of light, which is the fastest known speed in nature, and yet still painfully slow when stars are the points to be connected. In this region, interstellar travel becomes a problem of communication and isolation, because every increase in distance turns conversation into delay guidance, into autonomy, and shared presence into memory. Within the Earth-Moon system, communication delays are slight enough that they feel close to immediate by ordinary standards. Across the wider solar system, the delay grows, but mission control can still direct advise and respond within the course of a day. A probe near Mars may wait minutes for a signal to arrive. A probe near the outer planets may wait hours. These are significant intervals for navigation and operations, yet they remain part of a recognizable relationship between spacecraft and Earth. Humans on such missions, if they were ever sent that far, would still exist inside a broad frame of active contact with home. Interstellar distances change the scale completely. A message to the nearest star system takes years to arrive. A reply takes years more. No conversation in any ordinary human sense survives this structure. This delay alters the meaning of command. A spacecraft several light years away cannot depend on Earth for timely decisions during emergencies, repairs, navigation corrections, or medical crises. Instructions sent from Earth would arrive long after the event that required them. The crew must therefore become radically autonomous. Their ship must carry not only the tools for survival, but also the authority and knowledge needed to interpret problems and respond without outside confirmation. This increases the burden already placed on training, governance, computing, and social trust. A mission can no longer imagine Earth as an active supervisor. Earth becomes at best a distant archive of prior wisdom and a source of encouragement that arrives far too late to guide immediate action. Autonomy may sound manageable in principle. Human beings often value independence, and exploration has long included moments when travelers must act without help. Yet interstellar autonomy is of another order. It is not a temporary interval of isolation followed by quick reconnection. It is a permanent communication regime in which every exchange with Earth is separated by years. Even if the signal remains clear, the social meaning of that signal changes. A greeting is received long after the mood that inspired it has passed. Advice arrives after local decisions have already been made. News is always old. Grief may be learned years after the event. Celebration may be answered by people who have not yet, from the sender's perspective, heard the original success. Communication persists, but simultaneity disappears. This loss of simultaneity matters because human relationships depend heavily on shared time. Families, friendships, institutions, and cultures are held together not only by memory and language, but by ongoing mutual presence inside the same unfolding present. Interstellar delay breaks that condition. The crew may still love those on Earth, still remember them, still speak to them in recorded or transmitted form, but they no longer live in the same present. Their world and Earth's world separate into distinct time streams linked only by delayed echoes. As the mission progresses, the emotional content of communication may therefore become more difficult to bear. A message from home can comfort, but it can also intensify loss by reminding the receiver that the life described in the message is already irretrievably past. The problem deepens over long mission durations because Earth itself will change. Political systems may rise and fall, languages may shift, cultural references may fade, scientific understanding may advance. Institutions that launched the mission may no longer exist in recognizable form by the time the spacecraft is far on its way. A crew may continue to send reports to Earth, while receiving replies from descendants, successor institutions, or entirely altered societies. The continuity of the mission's original purpose may then weaken further. A ship launched by one civilization may arrive if it arrives at all under the observation of another. Communication delay thus becomes not only a technical barrier, but a civilizational one. The mission leaves not only a place but also a historical moment, and it cannot remain synchronized with either. The spacecraft's own internal communication must also be considered. In a small habitat, this may seem trivial, but as missions become more complex or multi-generational, internal communication becomes part of social stability. Technical knowledge must be preserved accurately across time. Maintenance procedures must be taught. Historical memory must be transmitted. Disputes about rules, mission goals, or risk cannot be settled by appeal to a distant authority that can respond promptly. The ship must therefore create its own durable systems of record education and interpretation. Archives may grow large, but information alone does not guarantee understanding. Meaning can drift. Ritual can replace reason. Technical language can become opaque to later generations if education weakens. A mission isolated by light-speed delay must protect not only its hardware but its knowledge culture. Artificial intelligence and advanced onboard computing may appear to offer relief. A sufficiently capable onboard system could assist with diagnosis, planning navigation, medical interpretation, and technical instruction. This may indeed be necessary for any long interstellar voyage. Yet such systems create their own concerns. They must remain reliable across very long durations. Their hardware must survive radiation and wear. Their software must remain interpretable and maintainable. If they become central to decision-making, the crew must trust them without becoming helplessly dependent on them. If they fail or behave unpredictably, there is no rapid external support. The more a mission depends on intelligent automation to replace Earth-based guidance, the more it must solve the long-term safety and governance of that automation inside the ship itself. Communication delay also transforms science during the voyage. A mission within the solar system can often send raw data home for analysis by large scientific teams using constantly updated tools and ideas. An interstellar mission must do far more science locally. Instruments may gather vast amounts of information, but bandwidth, power, and time constraints may make full transmission impractical. Decisions about what to study, what to preserve, and what to prioritize may need to be made aboard the vessel. If the mission is crewed, this further enlarges the need for broad expertise. If it is uncrewed, it raises the demand for sophisticated autonomy. In both cases, the delay to Earth turns exploration into local interpretation rather than shared real-time inquiry. There is also a strategic consequence. Rescue reinforcement and correction become almost meaningless at interstellar range. A problem detected on Earth cannot be answered with a rapid intervention. A new discovery about the target star or planet cannot be converted quickly into updated mission architecture. An unforeseen hazard encountered by the ship cannot be met by emergency launch. Every mission parameter must therefore be chosen before departure, with the understanding that later knowledge may arrive too late to matter. This gives the launch moment an unusual finality. A civilization sends the craft outward, and then in a practical sense lets go. This finality affects identity. The crew or inhabitants of the vessel must gradually come to see themselves not as an extension of Earth, under remote supervision, but as a separate human node carrying its own responsibilities and consequences. This may be necessary for morale and governance, but it also changes the nature of the mission. The farther the ship travels, the less it resembles an expedition connected by a long cord to home, and the more it resembles the beginning of a branch. That branch may remain emotionally tied to Earth, yet functionally it must live by its own judgment. Interstellar travel thus encourages separation not only by distance, but by the logic of delayed information. Independence is no longer a choice of style. It is imposed by physics. Scientific understanding supports this picture clearly. Communication at interstellar distance is limited by the speed of light, and no verified method exists to send useful information faster. Signal strength can be increased with power and better receivers, but power does not remove delay. Error correction can improve fidelity but not simultaneity. Quantum entanglement, despite frequent misunderstanding, does not provide a known means of faster-than-light communication. The barrier here is therefore firm. It is not a matter of waiting for stronger transmitters. It is a consequence of established physics. In this region, interstellar travel may be impossible for humanity, because it may require a level of separation from Earth that human missions cannot fully absorb without changing their nature. A voyage sustained across years of signal delay must carry its own lore, memory, expertise, and emotional world. It must survive without guidance that arrives in time to guide. It must accept that all messages from home are delayed fragments of a world already changed. The ship may continue to speak with Earth, but it does so across widening layers of lateness until contact remains real, yet no longer mutual in the ordinary sense. The stars ahead are distant, but so too is the home left behind. In the long silence between message and reply, the journey turns inward again. The ship becomes a world that cannot be corrected from outside, and humanity aboard it becomes something increasingly alone. If that degree of isolation breaks continuity, judgment, or allegiance, then the barrier to interstellar travel is not only physical distance. It is the slow severing of shared time by the finite speed of information. Even after a spacecraft has survived the long outward passage, another difficulty remains waiting at the destination. Reaching a star system is not the same as arriving in a useful way. A vehicle that has spent years or decades building enormous speed carries that speed with it. When the target star finally grows from a point into a system of worlds, dust, radiation, and gravity. Unless the craft can reduce its velocity substantially, it does not truly enter the system as a resident observer. It cuts through it as a passing object, gathering only brief glimpses before the chance is gone. In this region, interstellar travel becomes a problem of arrival deceleration and unknown conditions at the far end of the voyage. Deceleration is the forgotten twin of acceleration. Every difficulty involved in gaining high speed returns in some form when high speed must be shed. A spacecraft moving at a significant fraction of the speed of light carries an immense amount of kinetic energy. That energy cannot simply disappear when the destination is near. It must be redirected, radiated away, transferred to expelled mass, or otherwise managed through some physical process. If the mission uses onboard propulsion to slow down, then it must either carry additional propellant for this final phase, or reserve enough from the beginning which increases the launch burden and compounds the earlier mass problem. If it relies on an external method such as radiation pressure from the target star or interaction with the stellar wind or magnetic field, then the method must be strong enough, well-timed and compatible with the geometry of arrival. None of these options is simple. A fast flyby mission can avoid much of this burden. A small probe may streak through a system, gather data quickly, and transmit its results home over many years. This is scientifically valuable in principle, especially if the payload is modest, and the mission goal is observational rather than human settlement. Yet for humanity, a flyby is not enough. Human travellers cannot inspect a planet during a brief rush past and call the voyage fulfilled. They would need to remain orbit, descend, or otherwise establish a stable presence. This requires a controlled arrival. The spacecraft must slow from cruise speed to something that the destination system's gravity, orbit dynamics, and local environment can accommodate. Without that, the journey reaches another star only in the shallow sense of crossing its outer boundary. Precision navigation also becomes more demanding at the end of the voyage. Across several light years, even a tiny angular error can shift the spacecraft's path by a very large distance. Course corrections are possible during transit, but they consume resources and depend on reliable sensing and guidance. As the craft nears the target, it must distinguish among stars, planets, dust structures, and radiation conditions with high accuracy. A destination world may orbit close to its star or in an inclined plane, or in a system with multiple planets and complex gravitational interactions. The vehicle must arrive not merely at the right star, but at the right part of the star system, with the right timing and orientation, despite having made key decisions years earlier on the basis of incomplete and delayed knowledge. This incompleteness matters because exoplanet science, though increasingly powerful, does not yet provide the kind of intimate certainty that local mission planning enjoys within the solar system. Astronomers can infer planetary mass radius orbit atmospheric components in some cases and sometimes rough thermal or chemical characteristics. These are remarkable achievements. Yet they do not provide full surface-level confidence about winds, dust conditions, geology, toxic compounds, magnetic protection, biological hazards, mechanical landing conditions, or long-term habitability. A planet that appears promising from afar may prove hostile in detail. A thick atmosphere may contain corrosive chemistry. A surface may lack accessible water. Radiation may be intense because the star is active or the planet lacks a strong magnetic field. Gravity may be higher or lower than human physiology tolerates well over the long term. A destination may support no practical settlement at all. The target star itself may also pose hazards. Many small stars, especially red dwarfs, are known to produce flares and bursts of energetic radiation. A planet within the temperate zone around such a star may orbit very close to it, increasing exposure to stellar activity and raising the possibility of tidal locking where one side of the planet constantly faces the star. This does not automatically make the world uninhabitable, but it complicates the conditions under which atmosphere, climate, and surface water might remain stable. A spacecraft arriving after an interstellar crossing may therefore meet a system whose most interesting planets are also the most difficult to approach safely or inhabit comfortably. The nearer the star, the more its local character matters. If landing is considered, the challenge deepens further. Landing on a planet requires entry through atmosphere or descent to an airless body control of heat and speed and confidence in surface conditions. On Earth, and within the solar system, landings are rehearsed and guided by increasingly detailed observations. Even then they remain risky. At another star, the margin for uncertainty is much smaller because there is no easy retreat. A crew cannot simply sample multiple worlds freely. unless the mission architecture includes the fuel vehicles and support systems for such exploration. If the first chosen site proves unsuitable, the cost of correction may be too high. Arrival therefore demands not only slowing down, but making the right choices under uncertainty at the most consequential moment of the entire mission. Settlement, if imagined, is still harder than arrival. A habitable planet in the broad astronomical sense may not be a habitable home for human beings without vast technological support. Earth's biosphere is the product of billions of years of coevolution among atmosphere, oceans, rocks, microbes, plants, and animals. A distant planet with liquid water may still lack breathable air, familiar soils, useful biochemistry, manageable pathogens, or climate stability. Even if no native life exists, the absence of a functioning Earth-like biosphere means that settlers would still depend heavily on artificial habitats. In that case, the interstellar journey has not escaped the problem of sealed life support. It has only relocated it to another gravity well under less certain conditions. There is also the possibility that the destination contains life unlike Earth's. At present, no confirmed detection of extraterrestrial life exists, and it remains uncertain how common life may be beyond Earth. Yet if life does exist on a target world that does not simplify settlement, it may complicate it profoundly. Native organisms, if present, might be biochemically incompatible, ecologically disruptive, or dangerous in ways difficult to predict. Human microbes might also threaten any local biosphere. Ethical constraints would arise alongside practical ones. A planet already hosting life may not be an open refuge, but a place requiring protection from human intrusion and protection of humans from the planet's own unfamiliar biology. Even a mission whose goal is observation rather than colonization must survive the practical strain of operating in an unknown system. Instruments may face unexpected glare, dust, density, radiation bursts, or gravitational complexity. Autonomous decision-making becomes critical because Earth-based guidance arrives too late. A mission can prepare for broad classes of hazard, but it cannot prepare for every detail if the system is only partly known. The farther the journey, the more costly any unanticipated arrival condition becomes. An error at launch may be discovered too late. An error at arrival may be fatal. The destination, therefore, does not serve as a simple reward after the voyage. It presents its own concentrated version of the entire interstellar challenge. The craft must still protect life, or instruments still manage energy, still navigate precisely, and still function without timely help from Earth. The target star does not receive the travelers gently, merely because they have come far. It confronts them with local realities that may differ sharply from what distant telescopes suggested. Astronomy can narrow uncertainty, but it cannot yet abolish it for worlds many light years away. This is why interstellar travel may be impossible for humanity, even if the outward transit could somehow be endured. A successful mission must do more than cross a gulf. It must slow down, enter a system, identify viable options, survive unknown environmental conditions, and perhaps build a lasting presence in a place never touched before. Each of these demands rests on knowledge that is necessarily incomplete before departure. Each compounds the cost of failure, because there is no nearby rescue and no rapid revision from home. In this inward region, the dream of another world becomes most severe. The stars may seem like destinations when viewed from far away, but up close they are not abstractions. They are systems with difficult geometry, energetic local conditions, uncertain planets, and unforgiving consequences for error. To arrive is not merely to endure the road. It is to meet an unknown world with enough remaining strength, knowledge, and flexibility to stay. If humanity cannot guarantee that kind of arrival, then the end of the journey may be as impossible as the beginning. At the innermost boundary of the problem after distance speed, energy structure, ecology, biology, society, communication and arrival have each been examined in turn. One final question remains. It is no longer mainly about stars' engines or even the survival of a crew. It is about whether humanity can cross interstellar distance without ceasing to be the kind of civilization that set out in the first place. The deeper obstacle may not be a single physical barrier, but the combined strain of many barriers acting on one fragile species at once. In this region, interstellar travel becomes a test of continuity. Can a human mission remain physically viable, socially coherent, morally intelligible, and recognizably human across the full depth of the journey? Or does the attempt dissolve the very thing it seeks to carry? Each earlier layer has shown a form of mismatch. The stars are separated by distances that belong more naturally to light than to animal life. The medium between stars is sparse but not empty, turning high-speed motion into sustained exposure. The speed of light stands as the known upper bound on travel and communication. Energy demands rise steeply as useful speed increases. Rockets carry the burden of their own propellant. Advanced propulsion concepts remain uncertain, partial, or perhaps permanently impractical for large living payloads. Time itself becomes divided between travelers and those who remain. The spacecraft must survive without easy rescue. Life support must imitate parts of a planet without possessing a planet's scale. The body weakens, accumulates radiation damage and ages. Communities under confinement may fracture or lose purpose. Communication delay cuts the mission free from real-time guidance and shared history. Arrival demands slowing down into uncertainty rather than merely reaching a coordinate in space. None of these burdens is trivial in isolation. Together they may create a total difficulty greater than any one field can solve. This total difficulty matters because human civilization does not operate as a single seamless intelligence. It is distributed, unstable, and historically contingent. Knowledge is stored in institutions, archives, habits, and skilled communities that change over time. Industry depends on supply chains, political stability, education, energy systems, and public will. Even large projects on Earth are vulnerable to changing priorities and fragile coordination. An interstellar mission would demand the opposite of fragility. It would require steady commitment across long planning horizons, immense resource concentration, technical maturity in many domains at once, and resilience against disruption over spans that may exceed the political patience of ordinary states and the cultural memory of ordinary societies. A civilization capable of launching such a mission may not be capable of sustaining the conditions that make the mission meaningful. This is not simply an argument about weakness of will. It is an argument about the scale mismatch between human historical rhythms and interstellar demands. Civilizations rise, fragment, merge, and transform on timescales far shorter than stellar travel, unless propulsion enters realms not currently supported by demonstrated engineering. Languages evolve, values shift, economic systems reorganize, scientific paradigms advance. A mission prepared under one world order may depart under another, and arrive if it arrives in relation to a third. The continuity needed for interstellar travel is therefore not just the continuity of machinery, it is the continuity of intention and interpretation. Humanity must continue to understand why the mission matters, what obligations it creates, and what counts as success, even as generations pass and circumstances change. There is also an ethical narrowing at this innermost level. Interstellar travel for humanity would likely demand extraordinary concentration of wealth, materials, expertise, and long-term attention. Those resources would be drawn from a species still facing persistent needs on its home world, including ecological stability, health, inequality, conflict, and the management of its own technological power. This does not automatically mean that interstellar effort is unjustified. Human beings pursue knowledge and exploration for reasons that are not reducible to immediate necessity. Yet the scale of sacrifice involved would be real. A civilization must decide not only whether it can send people between stars, but whether it can do so without distorting its moral priorities or placing intolerable burdens on those who remain. The larger the project, the more these questions move from engineering into ethics. For multi-generational missions, the ethical issue becomes sharper still. Later generations would inherit confinement, risk, and duty without having chosen the original undertaking. Their lives would be shaped by a mission architecture designed by ancestors who believed the destination justified the cost. Whether such inheritance is acceptable remains deeply uncertain. Human societies already struggle to treat future generations justly even within one world. An interstellar vessel would compress that struggle into a closed environment where departure, descent, and alternative futures are all constrained. A mission may preserve biological descent while losing moral legitimacy in the eyes of those born along the way. If that happens, continuity breaks at the human center of the enterprise. The problem also reaches identity. What is being preserved in interstellar travel? Is it simply the survival of human genetic material, the extension of a technical civilization, the spread of intelligence, or the continuation of a particular cultural and moral form of life? These are not the same thing. A mission could succeed biologically while failing culturally. It could preserve knowledge while losing freedom. It could arrive with descendants who no longer identify with Earth, with the founding purpose, or even with the idea that they are travelers rather than inhabitants of an enclosed world. Humanity may survive in some narrow sense across the gulf, and yet fail to carry forward the very qualities that made the journey desirable. This possibility does not negate the value of all future attempts, but it does mean that success cannot be defined only by survival or arrival. There is a more practical version of the same concern. Every solution proposed for interstellar travel tends to shift the burden inward toward human adaptability. If propulsion remains hard, the mission duration lengthens. If duration lengthens, ecology, health, psychology, and governance become harder. If shielding is heavy, propulsion becomes harder again. If payload is reduced, habitability suffers. If artificial gravity is added, engineering grows more complex. If autonomy is deepened, internal social stability becomes more important. If communication fails to remain emotionally meaningful, motivation weakens. The system behaves less like a set of separable problems and more like a tightly coupled web in which improvement in one region often worsens another. This is one hallmark of practical impossibility. A task need not violate a single law to remain beyond reach. It may simply require too many difficult conditions to be satisfied simultaneously by one civilization, one machine, and one species. Scientific humility is important here. It remains possible that future knowledge will change part of this picture. New materials may improve shielding. Energy production may become more powerful and more controllable. Closed ecological systems may become more reliable. Artificial intelligence may strengthen autonomy without undermining human agency. Advanced propulsion may send small robotic probes to nearby stars within meaningful scientific timescales. Some of these developments are plausible. None should be dismissed merely because the challenge is severe. Yet present evidence does not show a clear path by which all required advances converge into safe, sustained, crewed interstellar travel for humanity. Observations and theory reveal many barriers with increasing detail. It remains uncertain whether those barriers can ever be jointly overcome. This uncertainty supports a calm conclusion rather than a dramatic one. Interstellar travel may be impossible for humanity not because the universe issues a single absolute prohibition, but because humanity may be the wrong scale of creature for the task. Human beings are finite-lived, socially delicate, biologically earth-shaped and technologically powerful, only through large systems that are themselves historically unstable. The stars, by contrast, are separated by distances that demand extraordinary speed, extraordinary endurance, and extraordinary continuity. The mismatch may be too deep. The cosmos may permit intelligence to imagine the stars, clearly study them carefully, and perhaps reach them with instruments while still denying a practical path for human bodies and human societies to follow. If so, this is not a failure of imagination. It is a recognition of form. Some realities can be known more easily than they can be entered. Mountains can be seen from far plains long before paths are found across them. The stars may represent a still greater version of that truth. Humanity may remain a species whose destiny unfolds mainly within one planetary cradle, extending its understanding outward through telescopes, probes, mathematics, and remote sensing while never crossing the deepest gulfs in person. Such an outcome would still contain grandeur. It would mean that knowledge outruns possession, that reverence can coexist with restraint, and that the measure of a civilization lies not only in how far it travels, but in how honestly it understands the conditions of existence. At this innermost boundary, then, the argument settles into a quiet shape. Interstellar travel may be impossible for humanity because every layer of the undertaking presses against a real limit: physical, energetic, ecological, biological, psychological, social, temporal, and moral. None alone is necessarily final. Together they may be. The ship, the crew, the society behind them, and the world ahead must all align across a span governed by the slow speed of matter, the finite speed of light, and the fragility of living systems. That alignment may never become stable enough to carry human beings safely from one star to another. In the end, the stars remain where they have always been, reachable by thought, by light, and perhaps by machines long before they are reachable by human life. The distance between wonder and arrival may be the true interstellar gulf. Humanity can look across it, measure it, model it, and dream across it. It may never cross it whole. The thought of the stars remains gentle even when the facts are severe. Across the night sky their light arrives without effort, crossing distances that living bodies may never cross. Human beings learn to measure those distances, to understand the matter between suns, to trace the limits set by energy, speed, time, and the delicate needs of life. With each layer of understanding, the journey grows clearer and harder at once. The dream does not disappear, but it changes shape. It becomes quieter, less like conquest, more like recognition. A species formed on one small world may not be diminished by this recognition. Earth is not made smaller because the stars remain far. Human curiosity is not made weaker because the body has limits. There is a kind of steadiness in accepting that knowledge and travel are not always equal. The mind can move through mathematics, observation, and patient inference into regions the body cannot safely follow. Telescopes can gather ancient light. Instruments can cross some of the dark. Thought can assemble distant systems into understanding. These are also forms of arrival, though not the kind once imagined in simple heroic terms. If interstellar travel remains beyond humanity, then the night sky still keeps its meaning. It remains a record of physical law of time, older than memory of processes larger than history. It invites study without promising possession. It offers perspective without comfort. In that calm distance, the stars continue to teach scale, patience, and restraint. They remind a planetary species that wonder does not depend on access, and that some frontiers may remain real precisely because they are never fully crossed. The dark between suns stays wide. The light continues to come. Humanity rests for a while beneath that light, learning what it can, carrying its brief warmth on one world and letting the farther fires remain where they are.